Hello and welcome to The Sleepy Scientist. If you enjoy slow, thoughtful explorations of the universe, take a moment to like the video and subscribe to the channel. It helps more curious minds find their way here. And before settling in, share where you're watching or listening from tonight. A quiet bedroom in London, a late train in Tokyo, a small town under open desert sky. Wherever you are, the same physical laws are operating around you. Gravity is holding you to the earth. Electromagnetism is carrying this voice to your device. The speed of light is exactly what it is, no matter the country, the continent, or the century. And that quiet consistency is where tonight's journey begins. Because it is easy to take this for granted. The world behaves, apples fall downward, stars burn according to precise nuclear reactions, electrons move in ways that can be written in compact mathematical form. The universe does not wake up and improvise new rules on a whim, but pause for a moment and consider how strange that actually is. Why does the universe obey laws at all? Why are there stable patterns instead of chaos? Why can the motion of planets be predicted centuries in advance? Why can the behavior of light be written in equations that fit on a page? Why is there structure instead of randomness? Physics is often concerned with what the laws are. Newton described gravity. Maxwell unified electricity and magnetism. Einstein reshaped gravity into geometry. Quantum mechanics revealed a probabilistic layer beneath classical certainty. Each advance refined the rules. But beneath all of that sits a deeper question. Not what the laws are, not how they operate, but why there are laws in the first place. Is the universe following commands? Or are these laws simply descriptions of regularities we've noticed? Are they fundamental features of reality? Or emergent patterns rising from something even deeper? Could the laws have been different? Could there have been no laws at all? The very existence of physical law implies stability. Stability allows atoms to form. Atoms allow chemistry. Chemistry allows stars, planets, oceans, and eventually observers capable of asking questions like this one. In that sense, the existence of law is not a small detail. It is the quiet foundation beneath everything familiar. And yet, the more physics progresses, the more subtle this question becomes. Modern theories suggest symmetry may underpin conservation laws. Quantum fields appear woven into the fabric of spacetime itself. The constants of nature carry precise values that shape cosmic history. Some cosmologists speculate about multiverses where laws vary. Others suggest that laws might emerge from deeper informational structures. But speculation aside, there is something undeniably remarkable already present. The universe is intelligible. It can be described. Its behavior can be captured in mathematics. Across billions of light years, the same principles apply. This raises an unsettling possibility. Perhaps law is not imposed from outside reality. Perhaps it is simply what reality is like at its most fundamental level. Structure rather than command. Pattern rather than prescription. Tonight's exploration will move slowly through this landscape. From the historical discovery of laws to symmetry and mathematics, to quantum mechanics and cosmology. From philosophical interpretations to the limits of explanation itself, there will be no dramatic revelations, no hidden conspiracies, only careful thought. Because sometimes the deepest mysteries are not explosive. They are quiet. They sit beneath everything, unnoticed precisely because they are so constant. The room around you feels solid because physical laws are stable. The device you are holding works because electromagnetic interactions are consistent. Your heartbeat depends on chemical processes governed by quantum mechanics. The stars above are fusing hydrogen according to the same nuclear rules that have operated for billions of years. The question is not whether laws exist, the question is why. And as the night settles in, and the familiar order of the world hums softly in the background, there is something calming about recognizing that stability. The same gravitational pull that guided ancient civilizations shapes the tides tonight. The same speed of light that illuminated the first galaxies carries information into your eyes at this moment. Perhaps lawfulness is the universe's most understated feature. Not dramatic, not loud, just consistent. So settle in. Let the question gently unfold. Why does the universe obey rules at all? And what might that tell us about the nature of reality itself? When physicists speak about a physical law, they're not referring to legislation written in a cosmic rulebook. There is no parliament of particles voting on amendments to gravity. A physical law is something quieter and more precise. It is a concise mathematical description of how some aspect of the universe behaves, consistently and reliably, under specified conditions. At its heart, a physical law captures a regularity. It states that whenever certain circumstances occur, certain outcomes follow, not because nature is obeying instructions, but because this is how nature consistently behaves. The law does not command the planets to orbit. It describes the pattern that planets trace through space. One of the clearest historical examples is Newton's law of universal gravitation, formulated by Isaac Newton in the late 17th century. In words, it states that the gravitational force between two masses is proportional to the product of their masses and inversely proportional to the square of the distance between them. In its familiar mathematical form, it can be spoken as force equals the gravitational constant multiplied by mass, 1 multiplied by mass 2 divided by distance squared. This compact statement successfully predicted the motion of falling apples, the orbits of the moon, and the trajectories of planets around the sun. But notice something subtle. The equation does not cause gravity. It does not push the Earth toward the sun. It is a distilled summary of observed behavior. It works extraordinarily well within its domain. It allowed astronomers to predict the existence of Neptune before it was directly observed. Yet it is still a description, not a prescription. A similar pattern appears in the 19th century with James Clerk Maxwell and the unification of electricity and magnetism. Maxwell's equations, written in 1865, describe how electric fields and magnetic fields interact and propagate through space. When expressed mathematically, they predict that disturbances in these fields travel at a specific speed. That speed turned out to match the measured speed of light. In other words, light itself is an electromagnetic wave. Again, the equations did not force light into existence. They revealed a deep regularity in how electric charges and magnetic fields behave. The beauty of Maxwell's work lies in how a small set of mathematical relationships unified phenomena that once seemed separate: static electricity, magnetism, and light. The law described what nature was already doing. The same pattern continues into quantum mechanics. The Schrödinger equation, introduced by Erwin Schrödinger in 1926, governs how the quantum state of a system evolves over time. In spoken form, it can be rendered as the imaginary constant multiplied by the reduced Planck, constant multiplied by the time rate of change of the wave function, equals the Hamiltonian operator acting on the wave function. Despite its abstract sound, this equation successfully predicts the energy levels of hydrogen atoms to astonishing precision. It underpins modern chemistry, semiconductor physics, and technologies such as magnetic resonance imaging. Yet even here, the equation does not instruct electrons how to behave. It encapsulates the pattern observed in countless experiments, from the double-slit experiment to atomic spectroscopy. This distinction between description and prescription is essential. A physical law is not a rule that the universe consults. It is a human formulation that captures stable, repeatable patterns in the behavior of matter, energy, space, and time. It is also important to clarify another common confusion. A scientific law is not the same as a scientific theory. In everyday speech, a theory sometimes means a guess. In science, a theory is a comprehensive, explanatory framework that accounts for a wide range of phenomena. The theory of general relativity, proposed by Albert Einstein in 1915, explains gravity as the curvature of spacetime. The theory of evolution by natural selection, developed by Charles Darwin in the 19th century, explains the diversity of life. Within a theory, there may be specific laws. Newton's law of gravitation was part of Newtonian mechanics, which functioned as a broader theoretical framework. Maxwell's equations sit within classical electromagnetism. The Schrödinger equation operates within the theory of quantum mechanics. Laws tend to be concise mathematical relationships. Theories provide the conceptual structure that explains why those relationships hold. Understanding this difference matters because when asking why physical laws exist, it is necessary to know what is being questioned. The inquiry is not about why equations are written on paper. It is about why the universe exhibits consistent mathematical regularities at all. These regularities are not trivial. The gravitational constant has a specific measured value. The charge of the electron is approximately 1.6 times 10 to the minus 19 coulombs. The speed of light in vacuum is approximately 300,000 kilometers per second. These numbers are woven into the structure of reality. If they were dramatically different, stars might not form, chemistry might not function, and stable matter might not exist. So the puzzle begins to sharpen. Physical laws are reliable, mathematically expressible patterns that apply universally, at least within observed domains. They are discovered through observation, experimentation, and mathematical reasoning. Institutions such as CERN, NASA, and the European Space Agency continuously test and refine them through particle collisions, satellite measurements, and astronomical observations. But are these laws features of reality itself, waiting to be uncovered? Or are they models constructed by human minds to compress vast amounts of data into manageable form? When Newton wrote down his gravitational law, did he discover something intrinsic to the universe, or did he invent a useful summary of observed motions? This is not a trivial philosophical diversion. If laws are discovered features of reality, then the universe has an inherent mathematical structure independent of observers. If they're constructed descriptions, then perhaps what exists fundamentally are events and interactions, and the laws are simply the most efficient way for human beings to describe patterns within them. The tension between these perspectives runs deep. Some philosophers of science, following David Hume, argue that laws are nothing more than regularities. Others maintain that laws reflect deeper necessities built into the fabric of nature. Modern physics, with its emphasis on symmetry principles and conservation laws, often suggests that certain structures are unavoidable once basic assumptions are made. Before exploring whether laws could have been different, or whether they emerge from deeper principles, it is essential to grasp what a law is and what it is not. A law is a precise, often mathematical, summary of consistent behavior observed in the universe. It is embedded within broader theoretical frameworks. It is tested, refined, and sometimes replaced when new evidence demands it. And yet, behind every equation, behind every successful prediction, there remains a quiet astonishment. The universe behaves in ways that can be captured in mathematics at all. The patterns are stable enough to discover. The regularities are consistent enough to trust. Whether discovered or constructed, physical laws point toward a world that is structured rather than chaotic. That structure is the real mystery. For much of human history, the world did not appear to run on precise mathematical laws. It appeared alive, intentional, and often unpredictable. Thunder was the voice of a god. The motion of the stars carried meaning. Stones fell because they sought their natural place. Fire rose because it belonged above. In ancient Greece, Aristotle developed one of the earliest systematic accounts of nature. His framework, written in the 4th century before the Common Era, divided the cosmos into two distinct realms. The terrestrial realm beneath the moon was the domain of change, decay, and imperfection. The celestial realm above the moon was perfect, eternal, and circular. Objects moved according to their natural motion. Earth and water moved downward. Air and fire moved upward. The heavens moved in perfect circles. This was not law in the modern sense. It was explanation rooted in purpose and essence. Motion was not described through equations but through qualitative reasoning. Aristotle's physics dominated European thought for nearly 2,000 years. It was coherent, intuitive, and largely consistent with everyday experience. Heavy objects did seem to fall faster. The heavens did seem distinct from earthly life. Yet this worldview left little room for universal mathematical regularity. It assumed difference rather than unity between sky and ground. The shift began gradually. In the 16th century, Nicholas Copernicus proposed a heliocentric model in which the Earth orbited the Sun. His model simplified certain astronomical calculations but retained circular orbits and epicycles. It was conceptual tremor rather than a revolution. The deeper transformation came with observation and measurement. Galileo Galilei, working in the early 17th century, turned telescopes toward the sky and discovered mountains on the moon, moons orbiting Jupiter, and phases of Venus. These observations challenged the Aristotelian distinction between celestial perfection and terrestrial imperfection. The moon was not a flawless sphere. Jupiter had its own satellites. The heavens were not fundamentally different from Earth. Galileo also transformed the study of motion. Through careful experiments with inclined planes, he demonstrated that objects accelerate uniformly under gravity, independent of their mass, when air resistance is negligible. The key principle he uncovered was that motion can be described quantitatively. Distance travelled increases in proportion to the square of time under constant acceleration. In spoken mathematical form, that relationship can be expressed as distance equals 1/2, multiplied by acceleration, multiplied by time squared. This was not merely a description of falling bodies. It was a declaration that nature follows measurable patterns. Johannes Kepler, building on the detailed astronomical data collected by Tycho Brahe, made an equally profound discovery. In the early 1700s, Kepler formulated 3 laws of planetary motion. Planets move in ellipses, not circles. A line connecting a planet to the Sun sweeps out equal areas in equal times. The square of a planet's orbital period is proportional to the cube of its average distance from the Sun. These were empirical laws derived from data, not philosophical speculation. Kepler did not know why these laws held. He searched for geometric harmonies and even mystical explanations. Yet the crucial shift had occurred. The motion of planets could be captured in precise mathematical relationships. the heavens were no longer governed by abstract perfection. They were governed by measurable regularity. The culmination arrived with Isaac Newton in 1687, when he published Philosophia Naturalis Principia Mathematica. In this work, Newton unified celestial and terrestrial motion under a single framework. The same gravitational force that pulls an apple toward the Earth also governs the orbit of the Moon. There was no longer one physics for the sky and another for the ground. There was one set of universal principles. Newton introduced 3 laws of motion and the law of universal gravitation. He demonstrated that Kepler's empirical laws could be derived from a deeper principle of inverse square gravitational attraction. For the first time, the cosmos appeared as a single, coherent system governed by mathematical laws that applied everywhere. This unification was more than technical. It reshaped human expectation. If the fall of an apple and the orbit of a planet obey the same principle, then perhaps all of nature operates under universal regularities. The scientific revolution reframed the universe as intelligible through mathematics. René Descartes, Gottfried Wilhelm Leibniz, and later Pierre-Simon Laplace embraced the idea that the universe could be understood as a vast mechanism. Laplace famously imagined an intelligence that, knowing the position and velocity of every particle at one moment, could predict the entire future and retrodict the entire past. This thought experiment captured the growing confidence in deterministic lawfulness. If laws are precise and universal, then the universe is in principle predictable. This intellectual transformation laid the groundwork for modern physics. It established a psychological assumption that order is normal. Today, it feels natural to expect that phenomena have underlying laws. When anomalies appear, the response is not to abandon the concept of law, but to search for a deeper one. When the orbit of Mercury deviated slightly from Newtonian predictions, the solution was not to discard gravity, but to refine it through Albert Einstein's general theory of relativity in 1915. The expectation of order has become so deeply embedded that its origin is often forgotten. It was not inevitable. It was constructed through centuries of observation, mathematical reasoning, and conceptual courage. The belief that nature is governed by universal mathematical regularities emerged slowly through telescopes, inclined planes, astronomical tables, and bold synthesis. There is something quietly astonishing about this shift. The night sky, once interpreted through myth and symbolism, became a domain of precise calculation. The falling stone, once explained through natural place, became a predictable outcome of gravitational acceleration. Order became the baseline assumption, and that assumption now shapes how questions are framed. When something behaves unpredictably, it is described as chaotic, but even chaos theory, developed in the 20th century by Edward Lorenz, operates within deterministic equations. Even turbulence follows mathematical patterns, though they may be complex. The historical journey from Aristotle to Newton did more than discover specific laws. It transformed the human relationship with nature. It replaced qualitative essence with quantitative structure. It replaced separate realms with universal principles. It cultivated the expectation that behind every phenomenon lies a pattern, waiting to be expressed in mathematical form. That expectation feels obvious now, but it is the product of a profound intellectual evolution. The universe did not announce its lawfulness. It was inferred, tested, and confirmed again and again, until order became the quiet, default assumption of modern thought. There is a quiet principle that runs beneath much of modern physics, often unnoticed because of its elegance. That principle is symmetry. In everyday language, symmetry suggests balance. A face may be roughly symmetrical from left to right. A snowflake may display rotational symmetry around its center. These are visual symmetries, patterns that remain unchanged when rotated or reflected. In physics, symmetry carries a deeper and more precise meaning. A system possesses symmetry if some transformation can be applied without changing the fundamental behavior of that system. The transformation might involve shifting position, rotating orientation, or moving forward in time. If the underlying laws remain the same after that transformation, the system is said to have symmetry. This idea may sound abstract, yet it lies at the foundation of modern theoretical physics. Consider time. If the laws of physics are the same today as they were yesterday, and will be tomorrow, then physics has time translation symmetry. Shifting the clock forward or backward does not alter the form of the laws. Experiments performed in 1900 or 2000 produce consistent results when conditions are controlled. The electron does not gradually change its charge over centuries. The gravitational attraction between two masses does not drift unpredictably with the calendar. Now consider space. If the laws of physics are identical in London, Nairobi, or on a spacecraft orbiting Mars, then physics has spatial translation symmetry. Shifting location does not alter the governing principles. Likewise, if rotating an experiment by 90 degrees or 180 degrees does not change its outcome, then physics has rotational symmetry. These symmetries are not decorative features, they carry profound consequences. In 1918, the mathematician Emmy Noether proved a theorem that forever links symmetry with conservation laws. Noether's theorem states that every continuous symmetry of the laws of physics corresponds to a conserved quantity. This statement is both simple and astonishing. If the laws of physics do not change over time, meaning they possess time translation symmetry, then energy is conserved. Energy cannot be created or destroyed in an isolated system. It may change form, from kinetic energy to heat, from chemical energy to light, but the total remains constant. If the laws do not depend on position in space, meaning they have spatial translation symmetry, then linear momentum is conserved. A spacecraft drifting through interplanetary space continues moving at constant velocity unless acted upon by an external force. Momentum remains constant because the underlying laws do not privilege one location over another. If the laws do not change under rotation, meaning they exhibit rotational symmetry, then angular momentum is conserved. A spinning figure skater pulling in their arms rotates faster. A collapsing cloud of gas in a forming star spins more rapidly as it contracts. These behaviors arise because angular momentum must be preserved. Noether's theorem reveals that conservation laws are not arbitrary add-ons. They are direct consequences of symmetry. Energy conservation is not simply a rule discovered by careful bookkeeping. It emerges because the universe does not treat one moment in time differently from another. This connection between symmetry and conservation provides a deeper layer beneath familiar laws. Instead of beginning with forces and writing equations of motion, modern physics often begins with symmetry principles. In quantum field theory, the framework underlying the standard model of particle physics, interactions are determined by symmetry requirements. Gauge symmetry, a central concept, dictates how fields transform under certain mathematical operations. The electromagnetic force arises from a symmetry known as U1 gauge symmetry. The strong nuclear force emerges from a more complex symmetry called SU3. These names refer to specific mathematical groups, but the essential idea is that the allowed interactions are constrained by symmetry. Physicists at institutions such as CERN do not simply ask which particles exist, they ask which symmetries nature respects. When a new particle is discovered, such as the Higgs boson in 2012, it confirms aspects of an underlying symmetry structure that had already been predicted decades earlier. Even Einstein's general theory of relativity is rooted in symmetry. The theory respects a principle called general covariance, meaning the laws take the same form under any smooth change of coordinates. This symmetry requirement leads directly to the geometric description of gravity as curvature of spacetime. In this way, symmetry acts as a guiding principle. Rather than observing forces and summarizing them, physicists often propose symmetry conditions first, then derive the mathematical consequences. The structure of the laws flows from the demand that certain transformations leave the fundamental description unchanged. This approach subtly reframes the question of why laws take the form they do. Perhaps they take that form because they must, given certain symmetries. Consider a simple analogy. A perfectly round sphere looks the same from any angle. Its symmetry restricts its possible shapes. In physics, if the universe is symmetric under time translation, it restricts the kinds of equations that can govern motion. The allowed laws are not limitless, they are constrained by invariance. Of course, symmetry in physics is not absolute. Symmetry breaking plays an equally important role. In the early universe, according to the Standard Model and cosmological theory, forces that are now distinct may once have been unified. As the universe cooled after the Big Bang, certain symmetries broke spontaneously. This symmetry breaking gave particles mass through the Higgs mechanism. It allowed distinct forces to emerge from a more unified state. Even here, symmetry remains central. The breaking of symmetry is itself governed by symmetrical principles. It is not chaos replacing order, it is a structured transition. Symmetry also shapes fundamental constants. The fact that the speed of light in vacuum is constant in all inertial frames is a symmetry principle at the heart of special relativity. Albert Einstein recognized in 1905 that the laws of physics should look the same to observers moving at constant velocity relative to one another. This symmetry requirement leads directly to time dilation and length contraction. It is not an afterthought. It is the foundation. There's a quiet elegance in this pattern. Instead of asking why energy is conserved, one can ask why time does not privilege one moment over another. Instead of asking why momentum persists, one can ask why space does not single out a preferred location. The answers trace back to invariance. Symmetry suggests that the form of physical law is not arbitrary. It may reflect deep structural features of reality. The universe appears indifferent to shift in position, orientation, and time. That indifference manifests as conservation laws and stable dynamics. This does not fully answer why symmetry exists. It shifts the question. Why does the universe possess these symmetries? Why are the laws invariant under transformation? These remain open philosophical and scientific questions. But symmetry offers something important. It provides an organizing principle that reduces apparent complexity. Instead of countless independent rules, there may be a small set of symmetry requirements from which much of physics follows. The hidden language of law may not be force or substance, but invariance, patterns that remain unchanged when viewed from different perspectives. A universe that does not care where or when an experiment is performed yields conservation laws automatically. In that sense, symmetry may not merely shape the laws, it may be the reason laws exist in the structured form they do. In 1960, the physicist Eugene Wigner published an essay with a title that has echoed through science and philosophy ever since. He called it The Unreasonable Effectiveness of Mathematics in the Natural Sciences. The phrase was not casual. Wigner was pointing to something deeply puzzling. Why should abstract mathematical structures, developed sometimes with no application in mind, so precisely describe the physical world? Mathematics often begins as pure thought. Complex numbers, for example, were once regarded as formal curiosities. They involve the square root of -1, a concept that has no direct physical counterpart in everyday experience. Yet complex numbers sit at the heart of quantum mechanics. The Schrödinger equation depends on them. Without complex numbers, the modern description of atomic structure would collapse. The same pattern appears elsewhere. Non-Euclidean geometry was developed in the 19th century by mathematicians such as Bernhard Riemann and Nikolai Lobachevsky. It was an exploration of what geometry would look like if Euclid's parallel postulate were altered. At the time, it seemed like an intellectual exercise. Decades later, Albert Einstein used Riemannian geometry to describe curved spacetime in general relativity. The mathematics was waiting, as though it had anticipated the needs of physics. Wigner's puzzle is not that mathematics works at all. Counting and measuring obviously require numerical tools. The deeper puzzle is that highly abstract, internally consistent mathematical systems often map onto physical reality with astonishing precision. The equations of quantum electrodynamics, refined by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, predict the magnetic moment of the electron correctly to more than 10 decimal places. That level of agreement between calculation and experiment is extraordinary. It suggests a profound alignment between mathematical structure and physical structure. How should this be understood? One philosophical response is Platonism. In the philosophy of mathematics, Platonism holds that mathematical entities exist independently of human minds. Numbers, sets, geometric objects, and algebraic structures are not invented. They are discovered. They inhabit an abstract realm that is timeless and non-physical. Under this view, when physicists write down equations that describe the universe, they are uncovering a mathematical reality that was always there. If Platonism is correct, then the effectiveness of mathematics is not unreasonable at all. The universe itself may be fundamentally mathematical. Physical laws might be instantiations of deeper mathematical truths. The cosmos would not merely obey equations, it would embody them. Another position is nominalism. Nominalists argue that mathematical objects do not exist independently. They are human constructs, useful fictions that help organize experience. According to this view, mathematics is a language created to describe patterns in the world. Its success arises because it has been refined to match observations. There is no separate mathematical realm. There are only physical processes and human descriptions. From a nominalist perspective, the effectiveness of mathematics is not mysterious. It works because it has been shaped by the demands of empirical success. The equations that survive are those that describe data accurately. Those that fail are discarded. Between these positions lies structural realism, a view developed within the philosophy of science in the 20th century. Structural realism suggests that what science captures correctly is not the intrinsic nature of objects, but the structure of relations between them. Under this interpretation, mathematics is effective because it mirrors relational structure. The universe may not consist fundamentally of particles with intrinsic properties, but of networks of relationships that can be captured mathematically. This perspective aligns closely with modern physics. In quantum field theory, particles are excitations of underlying fields. In general relativity, gravity is not a force but a manifestation of spacetime curvature. The emphasis shifts from substance to structure. mathematics becomes the natural language of relationships. The question then becomes more pointed. Does mathematical structure precede physical law, or does physical law give rise to mathematical structure? One possibility is that the universe has an intrinsic mathematical architecture. Physical law emerges because reality itself is structured in ways that correspond to mathematical systems. Under this view, the compactness of equations reflects a deep simplicity at the core of nature. The law of universal gravitation can be spoken as force equals the gravitational constant multiplied by mass 1 multiplied by mass 2 divided by distance squared. The simplicity of this relationship is not accidental. It mirrors a fundamental geometric symmetry of three-dimensional space. Another possibility is that mathematics emerges from the patterns observed in physical law. Human beings evolved in a world of stable regularities. Brains capable of recognizing pattern had survival advantages. Over time, abstract reasoning developed. Mathematics became increasingly sophisticated. Its alignment with physics may reflect cognitive adaptation to a structured environment rather than an independent mathematical realm. Yet this explanation feels incomplete. The mathematics used in modern theoretical physics often goes far beyond everyday pattern recognition. Tensor calculus, Hilbert spaces, group theory, and topology are not intuitive survival tools. They are abstract constructions that nevertheless describe black holes, subatomic particles, and the expansion of the universe. Why are physical laws expressible in compact mathematical form at all? Compactness is not trivial. The Einstein field equations, which describe how mass and energy curve spacetime, can be written in a single line of symbolic notation. When spoken, the equation becomes lengthy, but the underlying structure is concise. It states, in essence, that the curvature of spacetime is proportional to the energy and momentum present within it. This simple proportionality governs phenomena ranging from the bending of starlight near the sun to the expansion of the cosmos itself. The Schrödinger equation, despite its abstract appearance, can predict the spectral lines of hydrogen with remarkable accuracy. Those spectral lines have been measured in laboratories and observed in distant stars. The same mathematical relationship holds across billions of light years. The fact that such diverse phenomena can be captured by relatively compact equations suggests that the universe possesses underlying simplicity. Complexity arises from combinations and interactions, but the foundational rules are elegant. This elegance feeds back into the broader mystery. The universe is intelligible. It can be understood through reason, observation, and mathematical formulation. The intelligibility is not partial or local. It extends from the motion of galaxies to the behavior of electrons. One could imagine a universe in which patterns exist but are too irregular or too unstable to compress into equations. A universe in which every event requires a separate rule. Such a world would resist systematic understanding. Prediction would be nearly impossible. Science, as currently practiced, would not function. Instead, reality displays coherence. Symmetry principles lead to conservation laws. Differential equations describe motion. Probabilistic amplitudes predict quantum outcomes. Mathematics does not merely approximate. It often captures behavior with stunning precision. The question of whether mathematics is discovered or invented may never be settled conclusively. It may be that elements of both perspectives hold truth. Human beings invent symbolic systems, yet those systems sometimes reveal structures that feel as though they were waiting to be uncovered. What remains undeniable is the alignment itself. The patterns of the universe are not chaotic scribbles. They are structured in ways that correspond to mathematical relationships. Whether this reflects a Platonic realm, a structural feature of reality, or a refined descriptive language, the result is the same. Physical laws are written in mathematics because mathematics in some profound sense fits the world, and that fit, so natural that it is often overlooked, deepens the central mystery. Why should reality be intelligible at all? It is tempting to imagine physical laws as invisible rules imposed on matter. Gravity commands the moon to orbit. Electromagnetism instructs electrons how to move. The Schrödinger equation dictates the evolution of quantum states. This language feels natural because it mirrors how human societies function. Laws are written, laws are enforced, laws constrain behavior, but nature does not receive instructions. An electron does not consult Maxwell's equations before responding to an electric field. A planet does not check Newton's law of gravitation before curving through space. The equations are human formulations. They describe what consistently happens. They do not cause it to happen. This distinction may seem subtle, yet it changes the tone of the entire question. If physical laws are commands, then one might reasonably ask who or what enforces them. If they are descriptions, then the mystery shifts. The universe is not obeying laws. It is behaving in regular ways, and those regularities are captured in mathematical form. The philosopher David Hume, writing in the 18th century, offered one of the clearest expressions of this perspective. Hume argued that what are called laws of nature are simply regularities in experience. When events of one type are consistently followed by events of another type, the mind forms an expectation. For example, when heat is applied to water at standard atmospheric pressure, it boils at 100 degrees Celsius. After observing this repeatedly, one comes to expect it. Hume's regularity theory holds that there is no deeper necessity binding cause and effect beyond consistent conjunction. There is no invisible force compelling water to boil at that temperature. There is only the fact that, under those conditions, it always has. In this view, laws are summaries of the total pattern of events in the universe. They are compact ways of describing what actually occurs across space and time. They do not govern reality from outside. They supervene on the complete distribution of matter and events. This position is now known as humanism about laws. Modern philosophers such as David Lewis refined it further. Lewis proposed that the laws of nature are the axioms of the simplest and most informative description of the entire universe. According to this account, laws are part of what he called the best system that balances simplicity and explanatory power. Under humanism, there is no metaphysical glue holding events together beyond their regular arrangement. The universe simply unfolds in a certain pattern. Laws are the most economical summary of that pattern. Non-Humean accounts take a different approach. They argue that laws are more than descriptive summaries. According to non-Humean views, laws have a governing role. They express necessary connections in nature. Some philosophers suggest that laws are relations between universals, abstract properties that instantiate in particular objects. Others argue that laws are grounded in dispositions or powers intrinsic to entities. For example, under a dispositionalist view, mass has an inherent tendency to attract other masses. The gravitational interaction is not merely a pattern, it reflects a real causal power. The law of gravitation captures that power in mathematical form, but the power exists independently of the description. These competing perspectives shape how the original question is interpreted. If laws are governing necessities built into the fabric of reality, then asking why they exist becomes a deep metaphysical challenge. Why does the universe contain these particular necessary connections rather than others? If laws are descriptive regularities, the weight of the question shifts. The universe behaves in certain ways. Those behaviors can be summarized concisely. Asking why the summary exists may be less pressing than asking why the underlying pattern exists. Consider again the conservation of energy. In experimental physics, whether in laboratories at the National Institute of Standards and Technology or in particle collisions at CERN, energy appears conserved within measurement limits. The principle can be expressed as the total energy of an isolated system remains constant over time. Under a human view, this statement is a generalization of observed regularity. Under a non-human view, it reflects a deep necessity tied to time translation symmetry, as shown by Emmy Noether's theorem. The mathematical structure is the same. The metaphysical interpretation differs. Reframing laws as descriptions rather than commands softens the original puzzle. The universe does not require enforcement mechanisms. There is no need to imagine a cosmic authority ensuring compliance. Instead, there are stable patterns that can be represented in equations. This reframing also dissolves certain intuitive anxieties. The question, why does the universe obey laws, suggests a hierarchy in which laws stand above matter. The alternative phrasing, why does the universe display regular patterns, is quieter and perhaps more tractable. Yet the deeper mystery does not disappear. Even if laws are descriptions, the regularities themselves demand attention. Why is there consistent behavior rather than randomness? Why do conservation principles hold across billions of light years? Why does the Schrödinger equation predict atomic spectra so precisely? Humanism reminds us that laws do not float above reality. They are grounded in what actually happens. Non-humanism reminds us that patterns may reflect underlying necessities or powers. Between these views lies a space for further exploration. Perhaps laws are neither mere summaries nor external commands, but expressions of deeper structural features of reality. Perhaps what appears as regularity is rooted in symmetry, geometry, or informational constraints. The shift from commands to descriptions clears conceptual space. It removes anthropomorphic imagery and invites more careful metaphysical thinking. The universe does not consult rulebooks. It unfolds in patterns. Whether those patterns are contingent, necessary, emergent, or fundamental remains an open and quietly profound question. Some laws feel so basic that they seem untouchable. Energy is conserved. Momentum persists. The speed of light in vacuum is constant. These principles appear woven into the fabric of reality itself. It is natural to assume they are fundamental, meaning they exist at the deepest level and cannot be reduced to anything simpler. Yet physics has repeatedly shown that what appears fundamental at one scale can emerge from deeper processes at another. The concept of emergence refers to behavior at a large scale that arises from many small-scale interactions, even though it is not obvious from examining the individual parts in isolation. A single water molecule does not possess temperature. Temperature becomes meaningful only when enormous numbers of molecules are considered together. Likewise, pressure is not a property of an individual particle. It emerges from countless microscopic collisions. Thermodynamics provides one of the clearest examples. In the 19th century, scientists such as Sadi Carnot and Rudolf Clausius developed laws describing heat, work, and entropy. The second law of thermodynamics states that in an isolated system, entropy tends to increase over time. In spoken form, this can be summarized as the total entropy of an isolated system does not decrease. At first glance, this law appears absolute. It describes a universal tendency toward disorder. It explains why heat flows from hot objects to cold ones, why ice melts in a warm room, and why perpetual motion machines of the second kind are impossible. But Ludwig Boltzmann offered a radical reinterpretation. He showed that thermodynamic laws emerge statistically from the motion of enormous numbers of microscopic particles. A gas in a box contains on the order of 10 to the 23 molecules. Tracking each molecule individually would be impossible. Yet statistical mechanics allows the collective behavior to be described with simple laws. Boltzmann's famous entropy formula, expressed in words, is entropy equals Boltzmann's constant multiplied by the natural logarithm of the number of microscopic configurations consistent with the macroscopic state. This relationship connects the macroscopic concept of entropy to the number of microscopic arrangements of particles. Under this framework, the second law is not a strict prohibition. It is overwhelmingly probable behavior. Given the vast number of molecules involved, disordered states vastly outnumber ordered ones. It is not impossible for heat to spontaneously flow from cold to hot, but the probability is so small that it would not occur within the lifetime of the universe. This example demonstrates that a law once considered fundamental can emerge from deeper statistical behavior. The macroscopic regularity is real and reliable. It governs engines, stars, and biological systems. Yet it is not basic. It arises from molecular motion described by more fundamental dynamical equations. This raises an intriguing possibility. If thermodynamic laws emerge from microscopic mechanics, could what are currently regarded as fundamental laws also emerge from deeper structure? In condensed matter physics, this question is not speculative, it is practical. Consider superconductivity. When certain materials are cooled below a critical temperature, they conduct electricity without resistance. This phenomenon cannot be understood by examining a single electron. It arises from collective behavior described by the Bardeen-Cooper-Schrieffer theory, developed in 1957. Electrons pair up into what are called Cooper pairs and move coherently through the lattice. The emergent behavior displays new symmetry and new effective laws. Another example is the fractional quantum Hall effect, observed in 1982 by Daniel Suey and Horst Sturmer at Bell Laboratories, with theoretical explanation later by Robert Laughlin. In extremely strong magnetic fields and at very low temperatures, electrons in two-dimensional systems behave collectively in ways that produce quasi-particles with fractional electric charge. Fractional charge does not exist at the level of individual electrons. It emerges from the collective state. In these systems, entirely new effective particles and effective laws arise from interactions governed by more familiar underlying physics. The emergent laws are not illusions, they are measurable and precise, yet they are not fundamental in the same sense as the equations describing individual electrons. This layered structure suggests that nature may be organized hierarchically. At one level, quantum field theory describes fundamental particles and interactions. At a higher level, atomic physics describes atoms. Above that, chemistry describes molecular bonding. Then biology describes living systems. Each level has its own effective laws. Physicist Philip Anderson famously argued in his essay More is Different that each level of complexity brings new organizing principles that cannot be trivially reduced to lower levels. Emergence is not merely complexity. It involves new patterns and new regularities. If this is so, then asking whether physical laws are fundamental or emergent becomes subtle. Some laws, such as the conservation of energy, may be rooted in deep symmetry principles. Others, such as the second law of thermodynamics, clearly emerge statistically. Could even space-time itself be emergent? In certain approaches to quantum gravity, including ideas explored in string theory and loop quantum gravity, space-time geometry may arise from more fundamental quantum entities. The holographic principle, inspired by work on black hole thermodynamics by Jacob Bekenstein and Stephen Hawking, suggests that the information content of a region of space may be encoded on its boundary surface. This hints that geometry might not be primary. Research groups at institutions such as the Perimeter Institute for Theoretical Physics and the Institute for Advanced Study investigate whether space-time and gravity could emerge from quantum entanglement patterns. If so, the Einstein field equations might not be fundamental commands of the universe, but effective descriptions valid at large scales. Even the Standard Model of particle physics, tested extensively at CERN's Large Hadron Collider, may be an effective theory. It describes known particles and forces with remarkable accuracy, yet it contains parameters that appear arbitrary, such as particle masses and coupling constants. Some theorists suspect it emerges from a deeper framework not yet discovered. The possibility that laws themselves are emergent reframes the original question again. Instead of asking why the universe has these particular laws, one might ask what deeper structures give rise to them. The pattern becomes layered rather than absolute. Emergence also tempers the expectation of finality. A law that appears fundamental today may tomorrow be understood as a statistical consequence or an effective approximation. Yet emergence does not diminish the stability of observed laws. The second law of thermodynamics remains robust in practical terms. Superconductivity remains measurable. Conservation principles remain reliable. Emergent does not mean fragile. It means grounded in deeper processes. The distinction between fundamental and emergent invites a more dynamic view of physical law. Instead of imagining a fixed foundation with everything else built upon it, reality may resemble a hierarchy of effective descriptions, each valid within certain domains. Whether the deepest layer exists and whether it consists of mathematical structure, informational constraints, quantum fields, or something not yet conceived, remains uncertain. But the history of physics suggests caution before declaring any layer final. The laws that shape stars and atoms may themselves be the surface expression of deeper order. Even if the laws of physics are fixed and universal, they are not the whole story. Laws describe how systems evolve. They do not specify the exact state from which that evolution begins. For that, something else is required. Those something else are called initial conditions. A physical law can be thought of as a rule for change. Given a system in a particular state, the law tells how that state will develop over time. Newton's laws of motion, for example, determine how an object's position and velocity change under applied forces. But those laws do not tell where the object is located at the beginning, or how fast it is moving initially. Without that starting information, the future cannot be calculated. This distinction becomes especially important in cosmology. The Big Bang model describes the large-scale evolution of the universe. It rests on general relativity, proposed by Albert Einstein in 1915, and on the assumption that the universe is homogeneous and isotropic on large scales. The mathematical framework often used is the Friedmann equations, derived from Einstein's field equations. In spoken form, one of these relationships can be summarized as the rate of expansion of the universe depends on its energy density and spatial curvature. These equations determine how the cosmic scale factor, a measure of the size of the universe, changes over time. They describe expansion, deceleration, acceleration, and possible futures such as continued expansion or recollapse. Yet they do not uniquely specify what the universe looks like at a particular moment. They require initial conditions. Georges Lemaitre, a Belgian priest and physicist, was among the first to propose in the 1920s that the universe is expanding from a denser earlier state. He described a primeval atom, an early hot and compressed condition from which the cosmos evolved. Edwin Hubble's observations in 1929, showing that distant galaxies are receding with velocities proportional to their distance, provided strong empirical support for expansion. The law-like behavior here lies in the expansion dynamics governed by general relativity. The initial conditions lie in the specific energy density, temperature, and distribution of matter in the early universe. For example, measurements of the cosmic microwave background radiation, first detected by Arno Penzias and Robert Wilson in 1965, reveal that the early universe was extremely uniform, with temperature fluctuations at the level of roughly 1 part in 100,000. These tiny variations eventually grew under gravitational instability into galaxies and clusters of galaxies. The laws of gravity determined how density fluctuations evolved. The initial pattern of fluctuations determined which structures formed where. Laws shape the unfolding. Initial conditions shape the particular story. To use a simple analogy, consider a game of chess. The rules determine how pieces are allowed to move. They are fixed and universal. The starting arrangement of pieces determines the initial configuration. From there, many different games can unfold, even though the rules remain unchanged. The laws constrain possibilities. The initial conditions select among them. In cosmology, both elements are indispensable. Without laws, there is no consistent evolution. Without initial conditions, there is no specific universe to evolve. This distinction also clarifies certain philosophical tensions. When asking why the universe has the laws it does, one is asking about the governing equations. When asking why the universe has the particular large-scale structure it does, one is often asking about its initial conditions. The apparent fine-tuning of certain cosmological parameters illustrates this interplay. The density of matter in the early universe was extremely close to what is called the critical density, the value separating eventual recollapse from perpetual expansion. Small deviations from that value in the early moments after the Big Bang would have led to dramatically different cosmic histories. The laws of general relativity specify how density influences expansion. The specific early density value is part of the initial condition. Similarly, the arrow of time appears tied to an initial low entropy state. The second law of thermodynamics states that entropy tends to increase in isolated systems. For entropy to increase, it must begin relatively low. The observed large-scale smoothness of the early universe implies a very low gravitational entropy compared to what was possible. The laws allow entropy increase. The initial state determines the direction in which it unfolds. Why the universe began in such a low entropy condition remains an open question. Some proposals invoke cosmic inflation, a rapid expansion phase suggested by Alan Guth in 1981. Inflation can smooth out irregularities and drive the universe toward homogeneity. Yet even inflation requires certain initial conditions to begin. This layered structure of explanation hints at deeper issues. Laws tell how change occurs. Initial conditions tell what exists to change. Both contribute to structure. If the laws were chaotic or inconsistent, even simple initial conditions would not produce a stable cosmos. If the initial conditions were wildly irregular or constantly fluctuating without constraint, even elegant laws would not yield a coherent universe. A structured universe requires both consistent dynamical rules and a defined starting point. The question then becomes more refined. When asking why physical laws exist at all, one must distinguish that inquiry from asking why the universe began in a particular state. These are related but distinct puzzles. The laws describe possible evolutions. The initial conditions determine which path is taken through that possibility space. Together they produce stars, galaxies, planets, and observers capable of reflection. This interplay between law and starting point quietly shapes every cosmological model. It also prepares the ground for further reflection. If laws govern evolution and initial conditions select outcomes, one may wonder whether either of these elements could themselves arise from deeper principles. For now, it is enough to recognize that the existence of structure in the universe depends not only on lawfulness, but on a particular beginning. If there is a candidate for a fundamental description of nature, at least at accessible energies, it is what physicists call the standard model of particle physics. This framework, developed during the second half of the 20th century, describes the elementary particles and 3 of the 4 known fundamental interactions: the electromagnetic force, the weak nuclear force, and the strong nuclear force. The standard model does not include gravity. That omission is significant and unresolved. Yet within its domain, it has been tested with extraordinary precision. At its core, the standard model is built on quantum field theory. In this picture, the universe is not made primarily of tiny solid particles. Instead, it consists of underlying fields that fill all of space. An electron is not a little bead travelling through emptiness. It is an excitation, a ripple in an electron field. A photon is a ripple in the electromagnetic field. Every type of particle corresponds to a field that permeates the cosmos. Quantum field theory combines the principles of quantum mechanics with special relativity. It respects the requirement that no influence travels faster than light. It also incorporates the probabilistic structure of quantum theory, where outcomes are described in terms of amplitudes and probabilities. One of the defining features of the standard model is gauge symmetry. Gauge symmetry refers to certain transformations of the fields that leave the underlying physical predictions unchanged. These transformations are not spatial rotations or shifts in time. They involve changes in internal mathematical parameters associated with the fields themselves. In the case of electromagnetism, the relevant symmetry is known as U1 gauge symmetry. When the electron field undergoes a particular kind of phase change, the equations remain invariant provided the electromagnetic field transforms appropriately. Demanding this invariance leads directly to the existence of the electromagnetic interaction. In other words, the structure of the force emerges from the symmetry requirement. The weak nuclear force is associated with a more complex symmetry called SU2. The strong nuclear force, which binds quarks together inside protons and neutrons, is governed by SU3 gauge symmetry. These names refer to specific mathematical groups describing how internal transformations operate. The important point is that the allowed interactions are tightly constrained by symmetry. This symmetry-based structure was refined over decades by physicists such as Sheldon Glashow, Abdus Salam, and Steven Weinberg, who developed the electroweak theory in the 1960s. Their work unified the electromagnetic and weak forces into a single theoretical framework. Later, quantum chromodynamics described the strong force in terms of gluon fields interacting with quarks. Experiments at particle accelerators have repeatedly confirmed these predictions. At CERN, the European Organization for Nuclear Research, the Large Hadron Collider accelerates protons to energies of several trillion electron volts and collides them at nearly the speed of light. Detectors such as ATLAS and CMS analyze the debris from these collisions to test theoretical predictions. One of the most significant milestones occurred in 2012 when CERN announced the discovery of the Higgs boson. The Higgs field had been proposed in the 1960s by Peter Higgs and others as a mechanism for giving mass to elementary particles without violating gauge symmetry. In simple terms, the Higgs field interacts with certain particles, and the strength of that interaction determines their mass. The Higgs boson is a quantum excitation of that field. The discovery confirmed a crucial piece of the Standard Model. It demonstrated that spontaneous symmetry breaking occurs in the electroweak sector. At very high energies, the electromagnetic and weak forces are unified. As the universe cooled after the Big Bang, the symmetry broke and the forces became distinct. The Higgs field settled into a non-zero value throughout space, giving mass to particles such as the W and Z bosons. The mathematical structure underlying this framework is compact but intricate. The Lagrangian of the Standard Model, when written in full symbolic form, fits on a page. When spoken in words, it describes how fermion fields, such as quarks and leptons, interact with gauge fields corresponding to the electromagnetic, weak and strong forces, along with their couplings to the Higgs field. Despite its success, the Standard Model contains a striking feature. Many of its parameters appear arbitrary. There are particle masses that must be measured experimentally rather than predicted. The mass of the electron is approximately 0.51 mega-electron volts. The mass of the top quark is roughly 173 giga-electron volts. The strength of the strong force is characterized by a coupling constant whose value depends on energy scale. Altogether, the Standard Model includes more than 20 free parameters. These numbers are inserted into the equations to match experimental results. They are not derived from deeper principles within the theory itself. This arbitrariness raises deeper questions. Why do these constants have the values they do? Why are there exactly 3 generations of quarks and leptons? Why does the Higgs field have the particular vacuum expectation value that it does? Why does the strong force respect a property known as color confinement, preventing isolated quarks from being observed? From one perspective, the Standard Model represents a triumph of reductionism. It explains a vast range of phenomena, from nuclear reactions in stars to radioactive decay, using a small set of underlying fields and symmetries. From another perspective, it leaves unanswered why the universe selected this particular structure. The deeper puzzle emerges here. If laws are grounded in symmetry, and if symmetry constrains possible interactions, why does the universe exhibit these specific symmetries rather than others? Why U1, SU2, and SU3? Why not a different group structure? Why these particle content choices? Some theoretical approaches, such as grand-unified theories and string theory, attempt to embed the Standard Model within a larger symmetry framework. These proposals suggest that at extremely high energies, perhaps near what is called the Planck scale, additional symmetries unify the forces further. Yet experimental confirmation remains elusive. The Standard Model stands as both an endpoint and a signpost. It demonstrates that much of physical law can be derived from symmetry principles within quantum field theory. It also reveals that the apparent finality of a theory may conceal deeper layers. The fact that such a compact mathematical structure can describe the behavior of quarks, electrons, neutrinos, photons, gluons, and Higgs bosons across a vast range of energies is remarkable. It reinforces the sense that the universe possesses coherent underlying order. At the same time, the unexplained parameters suggest that the current framework may be effective rather than ultimate. The question shifts again. Are these laws fundamental, or are they emergent from a deeper theory not yet discovered? The standard model does not answer why there are laws at all. It clarifies the content of those laws at accessible scales. It narrows the field of possibilities. It shows that symmetry in quantum fields govern much of observable matter. But it also leaves open the possibility that what appears fundamental today may one day be seen as part of a larger, more unified structure. And in that space between precision and incompleteness, the question remains quietly present. Why this structure rather than another? In 1915, Albert Einstein completed a theory that reshaped the understanding of gravity. For more than 2 centuries, Isaac Newton's law of universal gravitation had described gravitational attraction as a force acting instantaneously across space. It worked remarkably well for planets, projectiles, and tides. Yet certain anomalies lingered, such as the precise precession of Mercury's orbit. Einstein approached the problem from a different angle. Instead of asking how masses pull on one another through space, he asked how mass and energy influence the structure of space and time themselves. The result was the general theory of relativity. At the heart of general relativity lies a radical idea. Gravity is not a force in the traditional sense. It is a manifestation of space-time curvature. Massive objects such as stars and planets curve the geometry of space-time around them. Other objects move along paths determined by that curvature. To understand this shift, it helps to clarify what is meant by space-time. In Special Relativity, published by Einstein in 1905, space and time are unified into a 4-dimensional continuum. Events are described not just by 3 spatial coordinates, but also by a time coordinate. The separation between 2 events depends on both spatial distance and temporal interval. General relativity extends this framework. It states that space-time is dynamic rather than fixed. It can bend, stretch, and curve in response to mass and energy. The mathematical language used to describe this curvature comes from differential geometry, particularly the work of Bernhard Riemann. The central equation of general relativity, known as the Einstein field equation, can be spoken in simplified form as the curvature of spacetime is proportional to the energy and momentum contained within it. More precisely, the equation relates the Einstein tensor, which encodes spacetime curvature, to the stress-energy tensor, which represents the distribution of mass, energy, pressure, and momentum. This relationship is not a metaphor. It is a precise mathematical statement tested through observation. When light passes near the Sun, its path bends slightly because space-time around the Sun is curved. This effect was first confirmed during the solar eclipse of 1919 by Arthur Eddington's expedition. Measurements showed that starlight passing near the Sun was deflected by the amount predicted by Einstein's equations, rather than by Newtonian gravity. Similarly, clocks run at different rates depending on gravitational potential. A clock placed on a mountain ticks slightly faster than one at sea level. This gravitational time dilation has been measured using atomic clocks with extraordinary precision. The Global Positioning System, which allows navigation satellites to provide accurate location data, must account for both special relativistic and general relativistic corrections. Without these adjustments, positional errors would accumulate at a rate of several kilometers per day. In this framework, objects in free fall are not being pulled by a force. They are following geodesics, the straightest possible path through curved space-time. Just as a great circle represents the shortest path on the surface of a sphere, a geodesic represents the natural path in curved space-time. This geometric interpretation shifts the meaning of law. The motion of planets around the Sun is not the result of a force acting across empty space. It is the natural consequence of moving through curved geometry. The Earth follows a geodesic in the spacetime shaped by the Sun's mass. The elegance of this formulation suggests something profound. The behaviour of matter is inseparable from the structure of spacetime itself. Law is not imposed from outside geometry. It is encoded within geometry. Black holes provide an extreme example. When a sufficiently massive star collapses under its own gravity, spacetime curvature becomes so intense that not even light can escape from within a certain boundary known as the event horizon. The Schwarzschild solution to the Einstein field equations describes this geometry precisely. The radius of the event horizon is proportional to the mass of the object. For the Sun, if compressed into a black hole, that radius would be about 3 kilometers. Gravitational waves offer another confirmation. Predicted by Einstein in 1916, gravitational waves are ripples in spacetime curvature generated by accelerating masses. In 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, directly detected these waves from the merger of two black holes more than 1 billion light-years away. The observed waveform matched the predictions of general relativity with remarkable accuracy. In all these cases, gravity is not an external push or pull. It is geometry in motion. This geometric framing tightens the link between law and inevitability. If spacetime has a certain structure, then motion follows naturally. The curvature determines the paths available. Objects respond not to commands, but to the shape of the arena in which they move. The inevitability here is subtle. Given the distribution of mass and energy, the curvature is determined by the Einstein field equations. Given that curvature, free objects follow geodesics. There is no additional instruction required. This suggests that physical law may be deeply rooted in structural necessity. If spacetime has certain symmetry properties and obeys certain geometric relationships, then behaviour unfolds accordingly. General relativity also shapes cosmology. The expansion of the universe described by the Friedmann equations emerges from applying Einstein's equations to a homogeneous and isotropic spacetime. The acceleration of that expansion, attributed to what is called dark energy, is inferred from observations of distant supernovae and the cosmic microwave background radiation. In each case, geometry governs evolution. The union of matter and spacetime in general relativity reinforces a central theme. Laws are not merely patterns overlaying a passive stage. The stage itself participates in the dynamics. Space and time are active elements in the unfolding of events. This integration raises further questions. Why does spacetime obey these geometric relations? Why does curvature respond to energy in precisely this proportional way? Could alternative geometries have existed? For now, what stands clear is that in general relativity, physical law becomes inseparable from spacetime structure. Gravity is geometry. Motion is guided by curvature. The fabric of reality is not a background. It is part of the law itself. And in that union of structure and behaviour, geometry begins to look less like a convenient language and more like an intrinsic feature of how the universe must be. Once the structure of physical law is laid out in equations and symmetries, another question naturally follows. Are these laws inevitable, or could they have been different? This question often centers on what physicists call fundamental constants. These are numerical values that appear in the equations of physics and must be measured experimentally. They include the speed of light in vacuum, the gravitational constant, the masses of elementary particles, and certain dimensionless numbers that shape the strength of interactions. One of the most discussed examples is the fine structure constant. This constant characterizes the strength of the electromagnetic interaction between charged particles. In approximate terms, Its value is about 1 divided by 137. Unlike the speed of light, which depends on the choice of units, the fine structure constant is dimensionless. It is a pure number. That makes it especially intriguing. The fine structure constant influences the structure of atoms. If it were significantly larger, electrons would bind more tightly to atomic nuclei. If it were much smaller, atoms might not hold together effectively. The chemistry that allows complex molecules to form depends delicately on this electromagnetic coupling strength. Another example involves the ratio of the electron mass to the proton mass. This ratio affects the size of atoms and the stability of chemical bonds. A substantial change could alter nuclear fusion processes inside stars. The gravitational constant also plays a role. If gravity were dramatically stronger relative to electromagnetism, stars would burn hotter and faster. If it were dramatically weaker, star formation might be inefficient. These observations lead to what is sometimes called the fine-tuning discussion. The phrase can sound dramatic, but the underlying issue is straightforward. Certain parameters of the Standard Model and cosmology appear to fall within ranges that permit long-lived stars, complex chemistry, and stable structures. Brandon Carter in the 1970s introduced what he called the Anthropic principle. The basic idea is modest. Observations of the universe are conditioned by the fact that observers exist. If certain physical constants were incompatible with the formation of galaxies, stars, and planets, then no observers would be present to notice those conditions. Therefore, the fact that the constants fall within life-permitting ranges is not surprising from the perspective of an observer. This anthropic reasoning does not claim that the universe was designed for life. It simply notes a selection effect. Out of a range of possible conditions, only those compatible with observers can be observed. Still, the deeper question persists. Are these constants free to vary in principle, or are they fixed by deeper mathematical necessity? In some theories, constants are not arbitrary at all. They arise from symmetry breaking or from boundary conditions imposed at extremely high energies. In certain approaches to grand unification, coupling constants converge toward a single value at very high energy scales. In string theory, additional spatial dimensions and geometric configurations may determine the values of constants through compactification mechanisms. Yet at present, no experimentally confirmed theory uniquely predicts all the parameters of the Standard Model. Their measured values are inputs rather than outputs. To explore whether alternative laws are physically possible, one must distinguish between logical possibility and physical possibility. Logically, one can imagine a universe with different constants, or even different numbers of spatial dimensions. In some speculative theoretical frameworks, such alternatives are mathematically consistent. For example, changing the number of spatial dimensions would alter the form of gravitational and electromagnetic laws. In 3 spatial dimensions, the inverse square law arises naturally from geometric considerations. In a universe with 4 spatial dimensions, the strength of gravity would decrease with the cube of distance rather than the square. That change would dramatically affect orbital stability. Planetary systems might not maintain long-term stable orbits. These considerations suggest that certain structural features of the universe may be tightly constrained by geometry itself. Other parameters may allow broader variation. The cosmological constant associated with dark energy provides another case. Observations of distant supernovae in the late 1990s revealed that the expansion of the universe is accelerating. The simplest explanation within general relativity involves a small positive cosmological constant. the measured value is extraordinarily small compared to theoretical estimates from quantum field theory. The discrepancy between predicted and observed values spans many orders of magnitude. If the cosmological constant were significantly larger and positive, the universe would have expanded so rapidly that matter would not have clumped into galaxies. If it were significantly negative, the universe might have recollapsed quickly. The observed value lies within a narrow range that allows structure formation. This convergence of seemingly sensitive parameters fuels curiosity about whether the laws could have been otherwise. One cautious approach is to acknowledge that current knowledge is incomplete. Some parameters that appear arbitrary may eventually be derived from deeper theory. What looks contingent today may prove necessary tomorrow. Another possibility is that the laws are not unique across all of reality. This suggestion leads toward multiverse hypotheses. In certain models of cosmic inflation, different regions of spacetime may undergo symmetry breaking in distinct ways, producing varied local constants. In string theory landscapes, different vacuum states may correspond to different effective laws. Under such scenarios, the observed constants in this universe would reflect local conditions rather than universal necessity. The anthropic principle would then operate across a broader ensemble. Whether such multiverse ideas correspond to physical reality remains an open question. Direct empirical evidence is challenging to obtain, yet the conceptual space has expanded. The question of whether laws could have been different touches on both physics and philosophy. It invites reflection on necessity and contingency. It probes the limits of explanation. What remains clear is that the laws as currently known are structured, precise, and deeply interwoven. Altering one parameter often has cascading consequences for atomic stability, stellar evolution, and cosmic history. Whether those parameters are fixed by deeper inevitability or selected among many possibilities is not yet resolved. The inquiry gently widens. If alternatives are conceivable within mathematical frameworks, perhaps the laws observed here are one realization among others. If they are uniquely determined by deeper structure, then necessity runs even deeper than currently understood. Either way, the possibility that laws might have been different sharpens the central question rather than dissolving it. In 1981, a young physicist named Alan Guth proposed a modification to the standard Big Bang model that would transform cosmology. He suggested that in the earliest fraction of a second after the beginning of cosmic expansion, the universe underwent a brief period of extremely rapid expansion known as inflation. During this phase, space itself expanded exponentially, doubling in size again and again in tiny fractions of a second. Inflation was introduced to solve specific problems. One was the horizon problem. Regions of the cosmic microwave background radiation, separated by vast distances in the sky, have nearly identical temperatures. Under the original Big Bang model without inflation, those regions would never have been in causal contact. Inflation resolves this by proposing that those regions were once much closer together before being stretched apart. Another issue was the flatness problem. Observations indicate that the large-scale geometry of the universe is very close to spatially flat. Inflation naturally drives the universe toward flatness, much as inflating a balloon makes its surface appear flatter over small patches. Inflation is not merely an add-on, it makes predictions that can be tested. Quantum fluctuations during inflation are thought to seed the tiny density variations observed in the cosmic microwave background radiation. Measurements by satellites such as the Wilkinson Microwave Anisotropy Probe and the Planck mission have confirmed patterns consistent with inflationary models. Yet inflation carries a deeper implication. In many versions of the theory, inflation does not end everywhere at once. Instead, it becomes eternal. Certain regions of spacetime stop inflating and form bubble universes, while inflation continues in other regions. The process repeats, producing a vast, possibly unending collection of causally disconnected regions. This idea is known as eternal inflation. In this framework, what is commonly called the universe becomes just one bubble within a much larger inflating background. Each bubble may have different effective physical constants or symmetry breaking patterns, depending on how fields settle into different vacuum states. This connects to another speculative development, the landscape of string theory. String theory proposes that fundamental particles are not point-like objects, but tiny vibrating strings. The theory naturally requires additional spatial dimensions beyond the familiar 3. These extra dimensions must be compactified, meaning curled up in tiny geometric shapes too small to detect directly. Different ways of compactifying these extra dimensions correspond to different vacuum states. Leonard Susskind and others have argued that the number of possible vacuum configurations in string theory may be extraordinarily large, sometimes estimated at around 10 to the 500 distinct possibilities. Each vacuum state could correspond to a universe with different effective constants and particle properties. When eternal inflation is combined with a large landscape of vacuum states, a multiverse scenario emerges. Different regions of spacetime may realize different low-energy laws. In some bubbles, the fine structure constant might differ slightly. In others, symmetry breaking might produce alternate particle spectra. It is important to emphasize that these ideas remain speculative. Inflation itself has strong empirical support for some of its predictions, but eternal inflation cannot currently be tested directly. The string landscape is a theoretical construction that has not yet been confirmed experimentally. The Large Hadron Collider at CERN has not produced evidence for supersymmetry or extra dimensions, which are often associated with string theoretic frameworks. Because different bubble universes would be causally disconnected, direct observation of other universes may be impossible in principle. That limits empirical access. Still, the multiverse hypothesis has gained attention because it offers a possible explanation for apparent fine-tuning. If many universes exist with different parameters, it is not surprising that at least some would fall within ranges compatible with structure and observers. The Anthropic principle then operates across this ensemble. In such a picture, the question, why do these laws exist, shifts to why do these laws exist here? The multiverse reframes the puzzle from uniqueness to selection, yet this reframing does not eliminate deeper questions. One may still ask why the overarching framework allows multiple vacuum states. Why does inflation occur? Why does the landscape have the structure it does? The existence of a multiverse would push the question one level higher rather than closing it. There is also philosophical caution. Some physicists and philosophers argue that a theory predicting unobservable universes risks moving beyond the bounds of empirical science. Others respond that if the underlying mathematical framework is well motivated and testable in other respects, then its broader implications deserve consideration. The multiverse hypothesis represents an attempt to take theoretical implications seriously. It arises not from imaginative storytelling, but from specific developments in quantum field theory, general relativity, and string theory. If correct, it would imply that physical law is not unique across all of reality. Instead, law would be local to particular regions within a larger structure. This possibility softens the apparent arbitrariness of constants in the standard model. They might not require unique explanation if many alternatives exist elsewhere. At the same time, the hypothesis leaves open whether the deeper framework itself is necessary or contingent. Why inflation? Why quantum fields? Why the mathematical structures that permit landscapes at all? The multiverse does not dissolve the question of law. It relocates it. Instead of asking why there are laws rather than none, one might ask why there is a meta-law permitting many variations. Why does the space of possibilities exist? Why is there a mechanism generating different effective descriptions? For now, the multiverse remains a proposal grounded in serious theoretical work but awaiting decisive empirical evidence. It expands the horizon of inquiry without settling it, and in expanding that horizon, it reveals that even the existence of many universes would not necessarily remove the deeper curiosity about why any lawful structure exists at all. At the beginning of the 20th century, physics encountered a domain where classical certainty began to dissolve. At atomic and subatomic scales, particles did not behave like tiny billiard balls following definite trajectories. Instead, their behavior was governed by quantum mechanics, a framework both mathematically precise and conceptually unsettling. One of the central equations of quantum mechanics is the Schrödinger equation, introduced by Erwin Schrödinger in 1926. In spoken form, it can be expressed as the imaginary constant multiplied by the reduced Planck, constant multiplied by the time rate of change of the wave function equals the Hamiltonian operator acting on the wave function. Although the words may sound abstract, the meaning is clear within the theory. The equation specifies how the wave function of a system evolves over time. The wave function is not a physical wave in space like a ripple on water. It is a mathematical object that encodes the probabilities of different possible outcomes when a measurement is made. For an electron in a hydrogen atom, the wave function determines the probability distribution for finding the electron at various positions around the nucleus. What is remarkable is that the Schrödinger equation is deterministic. Given a wave function at one time, its evolution is fully determined by the equation. There is no randomness in the mathematical evolution itself. Yet when a measurement occurs, outcomes appear probabilistic. The square of the wave function's magnitude gives the probability of observing a particular result. This is known as the Born rule, proposed by Max Born. If an experiment is repeated many times under identical conditions, the distribution of outcomes matches the predicted probabilities with extraordinary precision. This probabilistic character marks a departure from classical determinism. Werner Heisenberg in 1927 formulated the uncertainty principle. It states that certain pairs of physical quantities such as position and momentum cannot both be known with arbitrary precision simultaneously. In spoken form, it can be summarized as the uncertainty in position multiplied by the uncertainty in momentum is always greater than or equal to a small constant related to Planck's constant. This is not a limitation of measurement technology. It is a fundamental feature of quantum systems. The more precisely a particle's position is defined, the less precisely its momentum can be defined, and vice versa. The uncertainty principle reflects the wave-like nature of quantum objects. A perfectly localized wave would require an infinite range of momenta. Conversely, a wave with a single precise momentum would extend infinitely in space. Nature balances these properties. Does this indeterminacy undermine the concept of law? At first glance, probabilistic outcomes may seem to weaken the idea that the universe follows strict rules. If the result of a single radioactive decay event cannot be predicted with certainty, does that mean lawfulness has broken down? The answer depends on what is meant by law. The statistical predictions of quantum mechanics are among the most accurate in science. The half-life of a radioactive isotope can be measured and predicted with remarkable reliability. The probabilities of measurement outcomes follow precise mathematical distributions. The laws of quantum mechanics do not predict specific individual events. They predict the statistical structure of repeated events. The randomness is not lawlessness. It is structured unpredictability. This tension has led to multiple interpretations of quantum mechanics. The Copenhagen interpretation, associated with Niels Bohr and Werner Heisenberg, treats the wave function as a tool for calculating probabilities. According to this view, quantum systems do not possess definite properties prior to measurement. The act of measurement plays a fundamental role in defining outcomes. The theory does not describe an underlying deterministic reality beneath the probabilities. It describes what can be observed. The many worlds interpretation, proposed by Hugh Everett in 1957, offers a different picture. It maintains that the Schrödinger equation always governs evolution, without collapse. When a measurement occurs, the combined system of observer and observed evolves into a superposition of branches. Each branch corresponds to a different outcome, and all branches exist within a larger quantum state. From the perspective of an observer within one branch, a single outcome is experienced. Other interpretations include objective collapse theories, such as those proposed by Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber, which modify the Schrödinger equation to include spontaneous collapses and Bohmian mechanics, developed by David Bohm, which introduces hidden variables and deterministic particle trajectories guided by a pilot wave. Each interpretation preserves the empirical predictions of quantum mechanics. They differ in their metaphysical commitments. The existence of multiple interpretations highlights a key point. The mathematical law governing wave function evolution is precise and universally applied. The debate concerns what that mathematics represents. Does quantum indeterminacy mean that reality at its core is probabilistic? Or does it mean that the underlying structure is deterministic but inaccessible in certain respects? Either way, quantum mechanics reshapes the concept of law. Law is no longer synonymous with predictability of individual events. Instead, law can govern distributions and correlations. Experiments testing Bell's inequalities, beginning with John Bell's work in 1964 and later refined by Alain Aspect in the 1980s, have shown that local hidden variable theories cannot reproduce quantum predictions. These results confirm that quantum correlations exhibit non-local structure in a precise technical sense, though they do not allow faster-than-light communication. Quantum entanglement further illustrates that the properties of systems cannot always be understood independently. The state of a composite system may contain correlations not reducible to its parts. The law governing the whole differs from the simple sum of laws governing isolated components. In this quantum domain, law appears both strict and subtle. The Schrödinger equation applies universally. The probabilities follow exact mathematical rules, yet individual outcomes resist certainty. This duality invites reflection on the nature of necessity. Perhaps law does not require deterministic predictability. Perhaps it requires only stable structure at the level of statistical relationships. Quantum mechanics also introduces metaphysical uncertainty. If multiple interpretations remain viable, then the underlying ontology of reality is not yet fully settled. The mathematical formalism is clear. The meaning behind it remains debated. The existence of precise probabilistic laws suggests that order persists even when certainty fades. The structure is still there, encoded in wave functions and operators. The unpredictability lies in specific outcomes, not in the framework itself. In this way, quantum mechanics deepens rather than dissolves the question of law. It reveals that even at the smaller scales, behavior is not chaotic. It is governed by equations that have passed every experimental test to date. The mystery shifts from whether laws exist to what kind of laws they are: deterministic or probabilistic, governing or descriptive, unique or branching. At the quantum level, law remains present. It simply takes a form that challenges classical intuition. In the later decades of the 20th century, the physicist John Archibald Wheeler proposed a striking idea. He summarized it in 3 words: it from bit. By this he meant that physical reality, the it, might ultimately arise from information, the bit. According to Wheeler, every particle, every field, even spacetime itself, may at its core be rooted in yes or no answers to fundamental questions. The proposal was not casual speculation. Wheeler had spent decades working on general relativity, black hole physics, and quantum theory. He observed that in quantum mechanics, the act of measurement plays a crucial role. Outcomes become definite when information is obtained. This led him to wonder whether information is not merely a description of reality, but a foundational ingredient. To understand this shift, it helps to clarify what is meant by information in a technical sense. In 1948, Claude Shannon developed information theory while working at Bell Laboratories. Shannon defined information in terms of uncertainty reduction. If a message can take many possible forms, receiving the message reduces uncertainty about which form occurred. The amount of information can be quantified mathematically. Shannon's entropy formula, expressed in words, states, entropy equals -1 multiplied by the sum over all possible outcomes of the probability of each outcome multiplied by the logarithm of that probability. This formula measures the average uncertainty in a set of possible messages. The more unpredictable the message, the higher its informational entropy. This notion of entropy connects directly to thermodynamics. Ludwig Boltzmann's statistical definition of entropy relates macroscopic disorder to the number of microscopic configurations. Shannon's entropy quantifies uncertainty about states. Though developed in different contexts, both concepts measure the number of possibilities consistent with given constraints. In black hole physics, these ideas converge dramatically. In the 1970s, Jacob Bekenstein proposed that black holes possess entropy proportional to the area of their event horizon. Stephen Hawking later showed that black holes emit thermal radiation due to quantum effects near the horizon. The entropy of a black hole can be expressed in words as entropy equals 1/4 multiplied by the area of the event horizon divided by the square of the Planck length. This relationship suggests that information content is tied to surface area rather than volume. This led to the holographic principle, developed by Gerard 't Hooft and Leonard Susskind. The principle proposes that the information describing a volume of space may be encoded on its boundary surface. If true, space-time geometry and gravitational dynamics might emerge from deeper informational constraints. From this perspective, physical laws may not be primary. They may arise from the ways information can be stored, processed, and transformed. Quantum mechanics reinforces this connection. A quantum state encodes probabilities of outcomes. Entanglement represents correlations in information between systems. When 2 particles are entangled, measuring one provides information about the other, even if separated by large distances. The structure of quantum theory can be reformulated in terms of information processing tasks. Researchers in quantum information science, including scientists at institutions such as the Institute for Quantum Information and Matter at the California Institute of Technology, explore how entanglement entropy relates to spacetime geometry in certain theoretical models. In some formulations of quantum gravity, the geometry of spacetime appears to emerge from patterns of entanglement. If information is foundational, then laws might reflect constraints on how information can evolve. For example, the no-cloning theorem in quantum mechanics states that an arbitrary unknown quantum state cannot be copied perfectly. This limitation is not technological. It follows from the linearity of quantum evolution. It is an informational constraint embedded in the structure of the theory. Digital physics takes this idea further. Some theorists propose that the universe may be fundamentally discrete, composed of bits of information processed according to computational rules. Physicist Edward Fredkin and later Stephen Wolfram have suggested that simple computational rules might underlie complex physical behavior. In these views, space-time and matter emerge from underlying informational processes. These proposals remain speculative. There is no experimental confirmation that reality is literally a computer program. Yet the informational perspective has yielded fruitful insights in black hole thermodynamics, quantum error correction, and condensed matter physics. One striking example comes from the ADS-CFT correspondence, proposed by Juan Maldacena in 1997. This duality suggests that a gravitational theory in a higher dimensional spacetime can be equivalent to a quantum field theory without gravity in lower dimensions. The equivalence is expressed mathematically, but its implications are informational. Geometry in one description corresponds to quantum information patterns in another. If spacetime can be translated into entanglement structure, then geometry itself may be an emergent property of information. This shifts the question of law again. Instead of asking why certain equations govern fields and forces, one might ask what constraints are required for consistent information processing. If certain transformations of information are forbidden, certain symmetries may follow. If entropy must increase in closed systems, time asymmetry may emerge. The concept of law becomes intertwined with limits on information flow. The speed of light, for example, may represent not just a limit on motion, but a limit on causal information transfer. Quantum uncertainty may reflect limits on simultaneous knowledge of complementary variables. Under this informational lens, the universe appears less like a machine governed by rigid forces, and more like a network of informational relationships governed by consistency constraints. Whether this perspective is ultimate or merely metaphor remains debated. Some physicists view information as a useful description layered atop deeper physical entities. Others suspect it may be primary. What stands out is the increasing role of information in modern theoretical physics. From black hole entropy to quantum computing, informational concepts permeate fundamental discussions. If laws emerge from informational constraints, then the existence of law may reflect deeper requirements for coherent information structure. The universe must be internally consistent. It must avoid contradictions. It must preserve certain informational balances. In that sense, law may arise not from command but from consistency. The proposal that it comes from bit does not settle the question of why laws exist. It reframes it in terms of information. It suggests that beneath fields and particles, beneath geometry and force, there may lie a layer defined by possibilities, probabilities, and constraints on knowledge itself. Whether information is the final foundation or one more step in a deeper hierarchy remains open. But the idea gently expands the landscape. Physical law might not simply describe matter, it might describe the structure of information from which matter emerges. Time feels directional. Memories point toward the past. Expectations point toward the future. Ice cubes melt in warm rooms. Eggs scramble but do not spontaneously unscramble. This sense of temporal flow is so familiar that it often goes unquestioned. Yet many fundamental physical laws are time-symmetric. Newton's laws of motion, Maxwell's equations, and even the Schrödinger equation in quantum mechanics remain valid if time is mathematically reversed. If one were to film two billiard balls colliding and then play the footage backward, the reversed motion would still obey Newton's equations. Against this backdrop, the second law of thermodynamics stands out. The second law states, in clear form, that in an isolated system the total entropy does not decrease. Entropy is often described as a measure of disorder, but more precisely it measures the number of microscopic configurations consistent with the given macroscopic state. A highly ordered state corresponds to relatively few microscopic arrangements. A disordered state corresponds to many. If a box contains gas confined to one corner and a barrier is removed, the gas spreads to fill the entire volume. The number of possible molecular arrangements consistent with uniform distribution vastly exceeds the number corresponding to confinement in one corner. The spreading is overwhelmingly probable. The reverse process, spontaneous confinement, is not forbidden by the microscopic laws of motion. It is simply so statistically unlikely that it will not occur within realistic timescales. This statistical character was clarified by Ludwig Boltzmann in the 19th century. Boltzmann sought to derive thermodynamic behavior from the motion of individual molecules. His H-theorem attempted to show that a quantity related to entropy tends to decrease over time in certain systems, corresponding to entropy increase in thermodynamic terms. The H-theorem relies on assumptions about molecular chaos, meaning that particle velocities are uncorrelated before collisions. From these assumptions, Boltzmann demonstrated that systems naturally evolve toward equilibrium states with maximum entropy. The key insight is that the arrow of time emerges not from the fundamental equations themselves, but from statistical considerations combined with boundary conditions. At the microscopic level, the equations allow processes to run forward or backward. At the macroscopic level, the overwhelming dominance of high entropy states gives time its apparent direction. Entropy provides a bridge between probability and temporal asymmetry. Consider a simple deck of cards. There are an enormous number of possible shuffled arrangements, but only a small number of arrangements that appear ordered, such as all cards grouped by suit. If the deck is shuffled randomly, it will almost certainly move from an ordered state to a disordered one. The reverse transition is not impossible in principle, it is simply fantastically improbable. In thermodynamic systems, the number of microscopic configurations can be on the order of 10 raised to the power of 23 or more. With such enormous combinatorial possibilities, the statistical push toward equilibrium becomes effectively certain. This statistical nature of entropy connects directly to cosmology. The early universe, as inferred from measurements of the cosmic microwave background radiation, appears to have been in a state of very low gravitational entropy. Matter was distributed almost uniformly. As the universe expanded, small fluctuations grew into galaxies and clusters. Gravitational clumping increased entropy over time. The second law therefore depends on the initial condition of low entropy. If the universe had begun in a state of maximum entropy, there would be no direction for entropy to increase. Time would lack its familiar asymmetry. This reveals something subtle about law and time. The second law is not an absolute dynamical law in the same sense as Newton's equations. It is a statistical law conditioned on initial conditions. It holds with overwhelming probability given the structure of phase space and the early low entropy state. Temporal direction emerges from this combination. In daily life, the arrow of time manifests in countless ways. Heat flows from hotter objects to cooler ones. Biological organisms age. Information is recorded and accumulated. These processes all align with entropy increase. The fact that entropy tends to increase provides a physical basis for distinguishing past from future. Memory formation involves physical processes that increase entropy overall. The asymmetry of cause and effect aligns with thermodynamic asymmetry. This connection suggests that law existence is intertwined with temporal structure. If the universe lacked statistical regularities governing entropy, time might not exhibit direction in the familiar sense. The stability of macroscopic processes depends on the reliability of thermodynamic principles. The second law also underscores that not all laws are fundamental dynamical equations. Some are emergent, statistical regularities arising from large numbers of constituents. Their apparent inevitability reflects combinatorics rather than strict determinism. Yet their reliability is extraordinary. No laboratory experiment has ever demonstrated a spontaneous decrease of entropy in an isolated macroscopic system. The law remains one of the most robust principles in physics. This interplay between reversible microphysics and irreversible macrophysics highlights a layered view of law. The microscopic equations are time-symmetric. The macroscopic behavior exhibits asymmetry due to probability and initial conditions. Time's arrow, then, is not inserted into the equations by hand. It emerges from statistical structure. In that emergence, the existence of law takes on a temporal dimension. Laws do not merely describe static relationships. They govern change across time. The direction of that change reflects deeper statistical constraints. The universe unfolds in a way that makes the future different from the past. That difference is anchored not in arbitrary preference, but in the structure of entropy and probability. And within that structure, law and time are quietly interwoven. At some point in any deep inquiry, a quiet boundary appears. One explanation leads to another, which leads to another still. Gravity is explained by spacetime curvature. Spacetime curvature is described by the Einstein field equations. Those equations rest on symmetry principles and differential geometry. Geometry may emerge from quantum entanglement or informational structure. And then the question arises again, why that structure? This progression illustrates what philosophers call explanatory regress. For every answer, a further question can often be asked. Why this law? Because of symmetry. Why that symmetry? Because of deeper mathematical consistency. Why that consistency? The chain can continue. There are different ways to respond to this regress. One option is to search for a final foundational principle, from which all else follows. This aspiration has motivated unified theories throughout physics. If all forces and particles arise from a single underlying framework, perhaps the regress will terminate in necessity. Another possibility is that explanation must stop somewhere. There may be features of reality that admit no deeper reason. They simply are. The philosopher Bertrand Russell expressed a version of this idea in discussions about the existence of the universe. When asked why there is something rather than nothing, Russell replied that the universe may be a brute fact. By this he meant that it exists without further explanation. It does not require a reason beyond itself. Applying this perspective at a physical law suggests that certain laws may be brute facts. They might not be derivable from deeper principles. They might represent the bedrock of reality. This stance does not imply intellectual surrender. It acknowledges the possibility that explanation has limits. It is important to distinguish between scientific explanation and metaphysical explanation. Scientific explanation operates within the framework of empirical investigation. It seeks mechanisms, predictive models, and mathematical structures that account for observed phenomena. When general relativity explains the precession of Mercury's orbit, it does so by applying a geometric law to a measurable situation. Metaphysical explanation, by contrast, asks why the laws themselves hold. It seeks reasons for the existence of the framework rather than reasons within it. Physics is highly successful at providing explanations within the system of laws. It can describe how stars fuse hydrogen into helium through nuclear reactions governed by the strong and electromagnetic forces. It can calculate the energy output of the sun to remarkable precision. These are scientific explanations. When the question shifts to why the strong force has its particular coupling constant, or why spacetime has 4 dimensions rather than 3 or 5, the inquiry becomes more speculative. It moves toward metaphysical terrain. Some philosophers argue that the demand for ultimate explanation may be misplaced. Not every why question has a deeper answer. In mathematics, certain axioms are accepted without proof. From them, theorems are derived. In physics, certain empirical regularities may function as axioms of nature. Others maintain that deeper explanation is always possible in principle, even if currently inaccessible. They see apparent brute facts as temporary markers of incomplete understanding. The history of science offers examples of both perspectives. Newton treated gravity as an inverse square force without explaining its mechanism. Later, Einstein provided a geometric account. What once appeared fundamental was reinterpreted. Yet even Einstein's equations may not represent the final layer. There is also a logical caution. Explanatory chains cannot extend infinitely in a straightforward manner. If every law requires a deeper law to explain it, and that deeper law requires another, the regress never ends. At some point, either explanation bottoms out or it loops back into self-consistency. Self-consistency is one candidate for termination. Perhaps the deepest structure of reality is one that is mathematically coherent and free of contradiction. Under this view, the universe exists as a logically consistent structure, and further explanation is neither required nor meaningful. Another possibility is necessity grounded in mathematical structure. If only certain kinds of universes are logically consistent, then perhaps the laws we observe are among a narrow class of viable possibilities. Yet it is also possible that contingency plays a role. The universe may have features that are not derivable from first principles, but are simply given. Recognizing these limits invites intellectual humility. The existence of physical law may ultimately resist complete explanation. That does not diminish the power of physics. It clarifies its domain. Science excels at uncovering patterns, deriving consequences and testing predictions. It reveals extraordinary coherence across scales, from quantum fields to galactic clusters. It narrows possibilities and sharpens understanding. But the question of why there is law at all rather than none may rest at the boundary where scientific and metaphysical inquiry meet. Humility in this context does not imply resignation. It reflects awareness of the distinction between describing how the universe behaves and explaining why it exists in the form it does. The search for explanation has driven remarkable progress. It may continue to do so, yet there may always remain a horizon beyond which further reasons cannot be found. At that horizon, one encounters the possibility that some aspects of reality are simply the way they are. And in acknowledging that possibility, curiosity remains intact, tempered by an understanding that not every mystery yields to deeper derivation. There is a philosophical position that attempts to preserve the success of science while remaining cautious about what exactly is ultimately real. It is known as structural realism. Structural realism emerged in the 20th century as a response to a historical observation. Scientific theories often change dramatically over time. The transition from Newtonian gravity to Einstein's general relativity replaced the concept of gravitational force with spacetime curvature. The transition from classical mechanics to quantum mechanics reshaped the understanding of matter itself. If theories change so deeply, what confidence can there be that current descriptions capture the true nature of reality? Structural realism offers a careful answer. It suggests that what science captures reliably is not the intrinsic nature of objects, but the structure of relations between them. Even when theories are replaced, certain mathematical relationships survive. For example, Newton's inverse square law for gravity was superseded by Einstein's geometric description. Yet in weak gravitational fields and at low velocities, Einstein's equations reduced to Newton's law. The structural relationship between mass, distance, and gravitational effects is preserved in a limiting case. The deeper interpretation changes, but the relational pattern persists. Similarly, classical electromagnetism and quantum electrodynamics differ conceptually. One describes continuous fields, the other describes quantized excitations of fields. Yet Maxwell's equations remain embedded within the quantum theory as part of its classical limit. The structural relations between electric and magnetic fields survive. From this perspective, scientific progress does not reveal the intrinsic essence of electrons, quarks, or space-time. It reveals the web of relationships connecting measurable quantities. There are two main forms of structural realism. Epistemic structural realism holds that only structure is knowable, even if objects possess intrinsic properties beyond our reach. Ontic structural realism goes further. It proposes that structure is all there is. Objects do not possess independent existence apart from the relations in which they participate. Ontic structural realism finds resonance in modern physics. In quantum field theory, particles are not isolated entities. They are excitations of underlying fields. Their properties arise from interactions governed by gauge symmetries. An electron is defined not by hidden internal substance, but by how it couples to the electromagnetic field, how it responds to weak interactions, and how it transforms under symmetry operations. In general relativity, spacetime geometry is not a passive stage. It interacts dynamically with matter and energy. The curvature of spacetime depends on energy and momentum distribution. The structure of relations between events determines motion. Quantum entanglement pushes this relational view further. Two particles can exhibit correlations that cannot be explained by independent intrinsic properties alone. Their joint state contains relational information that defines measurable outcomes. The properties of the system are not reducible to the properties of its parts. From a structural realist standpoint, law is not something imposed upon independently existing objects. Law is the pattern of relations itself. The equations do not describe how things behave in addition to what they are. They describe the network of relations that constitutes what they are. This perspective dissolves certain metaphysical tensions. If laws are governing commands acting on substances, one must ask what enforces them. If laws are descriptive summaries of independent objects, one must explain why those objects happen to behave consistently. Structural realism reframes the situation. There are no isolated substances awaiting governance. There is relational structure from the outset. Regularity is built into that structure. Asking why the structure behaves consistently may be like asking why a geometric figure maintains its angles. The angles are part of what it is. This does not eliminate all mystery. One can still ask why this relational structure exists rather than another. Yet the need for external enforcement fades. Lawfulness becomes an expression of structural coherence. In mathematics, a triangle in Euclidean geometry necessarily has interior angles summing to 180 degrees. That property is not imposed from outside. It follows from the structure of Euclidean space. Similarly, certain physical behaviors may follow inevitably from the relational structure of fields and symmetries. Modern theoretical physics increasingly emphasizes symmetry groups, topological invariants, and geometric relationships. The language is relational rather than substantial. Fields interact through structured couplings. Particles transform under symmetry operations. Spacetime curvature encodes gravitational interaction. Under structural realism, these patterns are not secondary descriptions. They are the primary content of reality. This view prepares the ground for a broader synthesis. If relational structure is fundamental, then physical law may be indistinguishable from the structure itself. The question of why laws exist becomes closely tied to the question of why relational coherence exists. The universe may not consist of objects following rules. It may consist of structured relations that necessarily exhibit certain regularities. Within that framework, law and structure are not separate. They are two perspectives on the same underlying order. The word chaos often suggests complete disorder, a breakdown of structure, an absence of rule. In everyday language, chaos means confusion or unpredictability. Yet in physics and mathematics, chaos has a more precise meaning. It refers to systems that are governed by deterministic laws, but exhibit extreme sensitivity to initial conditions. The modern study of chaos in dynamical systems took shape in the 20th century. One of its central figures was Edward Lorenz, a meteorologist working in the early 1960s. Lorenz was using a simplified set of equations to model atmospheric convection. The equations were entirely deterministic. Given initial values, the future state of the system was fully determined. During one run of his computer model, Lorenz rounded an input value from 6 decimal places to 3. He expected the outcome to remain nearly identical. Instead, the resulting weather pattern diverged dramatically over time. This sensitivity to small differences became known as the butterfly effect, a phrase inspired by the metaphor that the flap of a butterfly's wings might influence the formation of a tornado weeks later. The equations Lorenz studied can be expressed in words as a set of coupled differential relationships describing how temperature difference, convective intensity, and horizontal temperature variation evolve over time. Despite their simplicity, the solutions trace complex, non-repeating patterns in phase space. The resulting structure, called the Lorenz attractor, has a distinctive shape resembling a butterfly. The key insight is that chaos does not imply absence of law. The system follows exact equations at every moment. The unpredictability arises because small uncertainties in initial conditions grow exponentially. Over long timescales, precise prediction becomes practically impossible, even though the underlying laws remain fixed. This distinction is crucial. Lawful unpredictability is not lawlessness. It is the behavior of systems that amplify tiny differences through nonlinear interactions. Nonlinearity plays a central role here. In linear systems, outputs are proportional to inputs. Small changes produce small effects. In nonlinear systems, interactions between components can produce feedback loops. A slight variation can cascade into large divergence. Weather is a classic example. The Navier-Stokes equations governing fluid dynamics are deterministic. Yet long-term weather forecasting remains limited because of chaotic sensitivity. The equations do not fail. They operate with precision. the limitation lies in the impossibility of measuring initial atmospheric conditions with infinite accuracy. This phenomenon extends beyond meteorology. Planetary orbits in multi-body systems can exhibit chaotic behavior over long timescales. Certain ecological populations fluctuate unpredictably under deterministic growth equations. Even simple mathematical maps, such as the logistic map, display chaotic regimes when parameters cross certain thresholds. The logistic map can be spoken in words as the next value equals a growth parameter multiplied by the current value multiplied by 1 minus the current value. For certain ranges of the growth parameter, the system settles into stable equilibrium. For other ranges, it oscillates. For still higher values, it becomes chaotic, never repeating yet always confined within specific bounds. This bounded unpredictability reveals an important point. Chaotic systems often possess attractors, regions of state space toward which trajectories converge. The Lorentz attractor, though complex, constrains motion within a finite region. Stability and unpredictability coexist. Randomness, too, must be distinguished carefully. In classical chaotic systems, randomness arises from sensitivity to initial conditions, not from indeterminism. In quantum mechanics, randomness appears intrinsic at the level of measurement outcomes, yet it follows precise probability laws. Neither classical chaos nor quantum randomness implies absence of structure. Both operate within mathematical frameworks that impose constraints and regularities. The broader question then becomes sharper. Why does the universe display structured dynamics rather than pure disorder? Even chaotic systems remain lawful. Their unpredictability emerges from complexity, not from absence of rule. One can imagine a hypothetical universe in which events occur without consistent pattern, where no stable regularities persist long enough to formulate equations. In such a world, stars might flicker unpredictably. Chemical bonds might form and break without statistical pattern, and memory itself might be impossible. Instead, the actual universe displays layered order. At small scales, quantum probabilities follow strict distributions. At larger scales, classical mechanics governs motion with predictable precision in many contexts. Chaotic systems amplify variation but remain bounded by law. Stability arises not from the absence of fluctuation, but from the presence of consistent structure. A stable solar system can exist even if minor gravitational perturbations introduce chaotic elements over billions of years. The Earth's climate can vary unpredictably from day to day, while maintaining long-term energy balance governed by thermodynamic constraints. This coexistence of order and unpredictability suggests that lawfulness provides the framework within which complexity unfolds. Chaos does not replace law. It operates inside it. The presence of deterministic chaos demonstrates that unpredictability does not require violation of physical principles. It emerges naturally from nonlinear interactions. In this sense, the question, why order rather than chaos, may rest on a misunderstanding. Chaos itself depends on order. Without fixed equations, there would be no sensitivity to initial conditions. Without defined dynamical rules, there would be no attractors. Lawful unpredictability contributes to richness. It allows weather patterns, ecological dynamics, and even aspects of neural activity to exhibit variation without collapsing into incoherence. The universe appears neither rigidly mechanical nor arbitrarily random. It is structured yet dynamic, predictable in principle at certain scales, sensitive and intricate at others. Within this layered structure, order and chaos are not opposites. They are intertwined expressions of underlying law. Physical laws do not descend from pure thought alone. They are inferred from repeated observation, careful measurement, and deliberate testing. The process is gradual and disciplined. A pattern is noticed. A hypothesis is formed. Predictions are made. Experiments are performed. The cycle repeats. When Isaac Newton formulated the law of universal gravitation, he did not invent planetary motion. He studied astronomical observations, including Johannes Kepler's empirical laws, and sought a mathematical relationship that accounted for them. When James Clerk Maxwell unified electricity and magnetism, he relied on decades of experimental results from researchers such as Michael Faraday. Observation anchors theory. Yet observation alone does not automatically produce law. Data can be messy, incomplete, and noisy. The scientific method provides structure for interpreting it. Karl Popper, a 20th century philosopher of science, emphasized falsifiability as a defining feature of scientific theories. According to Popper, a scientific statement must be testable in a way that could, in principle, prove it wrong. A claim that accommodates every possible outcome does not constrain reality, and therefore does not function as a scientific law. Under this view, the strength of a law lies not in how confidently it is asserted, but in how rigorously it survives attempts at refutation. Newtonian mechanics was tested in countless experiments. Eventually, discrepancies such as the precession of Mercury's orbit revealed limits to its domain of validity. General relativity replaced it in certain regimes, yet Newton's equations remain accurate approximations at everyday speeds and gravitational strengths. This pattern illustrates an important principle. Laws in science are provisional models. They are not absolute declarations. They are the best available descriptions given current evidence. Consider the Standard Model of particle physics. It has been tested in particle accelerators around the world, especially at CERN with the Large Hadron Collider. High-energy proton collisions produce showers of particles, and detectors record their properties with extraordinary precision. The measured cross-sections, decay rates, and scattering amplitudes align with theoretical predictions to many significant figures. Yet physicists continue to probe for deviations. Measurements of the muon's magnetic moment, for example, have been conducted at facilities such as Fermilab to search for discrepancies that might hint at new physics beyond the Standard Model. The process is ongoing. Similarly, NASA and other space agencies refine gravitational models through satellite observations and deep space missions. The trajectories of spacecraft navigating near planets provide sensitive tests of general relativity. Gravitational wave observatories such as LIGO and Virgo analyze signals from distant black hole mergers, comparing waveforms to theoretical predictions. Each successful test strengthens confidence. Each anomaly invites revision. The role of observation therefore grounds law in empirical reality. Without repeated confirmation, equations remain speculative. With sustained verification across domains, they gain credibility. This empirical grounding also enforces humility. Scientific knowledge is not immune to revision. The history of physics includes shifts from Aristotle's natural motion to Newtonian mechanics, from Newtonian gravity to Einsteinian curvature, from classical determinism to quantum probability. At each stage, earlier models were not discarded as useless. They were recognized as limited. Newton's law of gravitation still predicts satellite orbits accurately. Classical electromagnetism still describes radio transmission. The refinement lies in recognizing domain boundaries. Epistemic humility means acknowledging the distinction between confidence and certainty. A law may be supported by overwhelming evidence and still remain open to refinement. It may describe observed phenomena with remarkable precision while leaving deeper questions unanswered. The measurement of the speed of light, for instance, has been refined repeatedly through improved instrumentation. Today, its value in vacuum is fixed by definition within the International System of Units. Yet that convention rests on a history of experimental work stretching back to the 19th century. Laws are therefore collaborative achievements. They are shaped by generations of researchers, by institutions, by peer review, and by technological advancement. Large scientific collaborations involve hundreds or thousands of scientists working together to test predictions and analyze data. Observation does not merely confirm law, it constrains it. It limits speculation. It narrows theoretical possibilities. At the same time, observation is theory-laden. Instruments are designed based on prior understanding. Data is interpreted within conceptual frameworks. There is interplay between theory and measurement. This dynamic relationship reinforces a central insight. Physical laws are not discovered once and for all in pristine form. They are approximated, tested, revised, and sometimes replaced. They are refined descriptions of consistent patterns in the natural world. Recognizing this process tempers grand claims. It does not diminish the achievement of science, it clarifies its character. Laws are powerful because they survive testing. They remain credible because they are open to challenge. In that openness lies both strength and humility. When asking whether physical laws are necessary, the question moves into the language of modality. In philosophy, modality concerns what is possible, what is necessary, and what is contingent. A statement is logically necessary if it could not be otherwise in any logically coherent world. A statement is contingent if it happens to be true, but could have been false without contradiction. The proposition that 2 + 2 = 4 is often treated as logically necessary within standard arithmetic. It does not depend on the structure of the physical universe. It follows from definitions and axioms. The proposition that the speed of light in vacuum is approximately 300,000 kilometers per second is different. It appears to be a physical fact. It could be imagined to have a different value without immediate logical contradiction. That suggests contingency rather than logical necessity. Some philosophers, such as David Lewis, developed a view known as modal realism. Lewis proposed that possible worlds are as real as the actual world, though causally disconnected. Under modal realism, what is possible corresponds to what occurs in some other world. In that framework, laws may vary across worlds. The laws in this universe would be contingent relative to the broader space of possibilities. Whether modal realism corresponds to physical reality is deeply debated, yet the concept clarifies the distinction between logical necessity and physical necessity. Physical necessity refers to what must happen given the laws of a particular universe. Within general relativity, for example, if a mass compresses within its Schwarzschild radius, a black hole forms. That outcome is physically necessary under those laws, yet those laws themselves might not be logically necessary. This distinction matters. A law may be necessary relative to deeper principles while still being contingent in a broader sense. One way to narrow the space of contingency is to ask whether mathematics constrains possibility space. If only certain mathematical structures are self-consistent, then perhaps only certain kinds of universes are possible. For example, the inverse square form of gravity in 3 spatial dimensions arises from geometric considerations. In a universe with 3 spatial dimensions, the surface area of a sphere grows in proportion to the square of its radius. A force spreading uniformly through space naturally weakens with the square of distance. This relationship reflects geometry rather than arbitrary choice. Similarly, gauge symmetry principles constrain allowed interactions in quantum field theory. Demanding local invariance under certain transformations leads to specific forms of coupling between fields. The structure of group theory limits the types of symmetries available. These constraints suggest that not every imaginable law is mathematically viable. Consistency, symmetry, and stability restrict the landscape of possible laws. However, restriction does not imply uniqueness. Multiple consistent mathematical frameworks may exist. String theory, landscapes, and other speculative models suggest many consistent vacuum states. Whether only one such state corresponds to a physically realized universe remains unknown. Metaphysical necessity would imply that the laws could not have been otherwise in any possible world. Physical necessity implies that given deeper conditions, certain outcomes follow inevitably. Logical necessity implies contradiction if denied. The current state of knowledge does not clearly establish that the laws of physics are logically necessary. They appear tightly constrained by mathematics and symmetry. Yet alternative consistent structures are conceivable. One might then ask whether the ultimate structure of reality, whatever it may be, is necessary in a deeper sense. If a final theory were discovered that left no free parameters and no alternative consistent solutions, that might suggest metaphysical necessity. But this remains speculative. For now, physical laws seem to occupy an intermediate status. They are not arbitrary in the sense of being unconstrained. They are not logically necessary in the strictest sense known. They are structured, coherent, and deeply interwoven. This recognition leads towards synthesis. The universe exhibits lawful regularity grounded in mathematical structure. Whether that structure is the only possible one or one among many remains uncertain. What stands clear is that lawfulness is not superficial. It is embedded in symmetry, geometry, probability, and information. It shapes time, stability, and complexity. The question of necessity does not yield a simple answer. It opens a space between inevitability and contingency. And within that space, reflection continues without urgency. A lawful universe is one in which patterns persist. Predictability becomes possible because equations remain stable across time and space. Conservation laws preserve energy and momentum. Quantum probabilities follow precise distributions. Spacetime curvature guides motion consistently. Without such stability, stars would not sustain nuclear fusion for billions of years. Hydrogen would not reliably fuse into helium through the strong nuclear interaction. The electromagnetic force would not bind electrons into atoms with predictable energy levels. Chemistry would lack structure. Complex molecules, including those central to life, would not form. The existence of physical law allows predictability at many scales. Engineers design bridges using principles of mechanics. Space agencies calculate orbital trajectories years in advance. Biologists model metabolic processes grounded in thermodynamic constraints. Stability does not imply rigidity. Quantum fluctuations seed cosmic structure. Chaotic dynamics introduce variation. Yet beneath these variations lies consistent rule. This consistency enables complexity. A star's steady radiation provides energy gradients that power planetary climates. Chemical regularities permit the formation of DNA and proteins. Neural activity in brains unfolds according to electrochemical laws. Understanding arises because patterns exist. Scientific inquiry depends on repeatability. If experiments yielded entirely unrelated outcomes under identical conditions, knowledge could not accumulate. The historical journey from Aristotle to Einstein, from Maxwell to the Standard Model, reveals a universe that is structured in ways accessible to mathematics. Symmetry principles lead to conservation laws. Geometry shapes gravity. Statistical mechanics explains entropy. Quantum theory encodes probability in precise form. Philosophical reflection refines this picture. Laws may be descriptive rather than prescriptive. They may emerge from deeper structure. They may be constrained by mathematics. They may not require further explanation beyond coherence. Living in a lawful universe means inhabiting a reality where change is patterned. It means that memory is possible because processes are reliable. It means that observation can reveal regularity. It means that prediction, though limited, is meaningful. Lawfulness is the quiet background that allows everything else to unfold. Stars ignite because nuclear physics operates consistently. Galaxies rotate according to gravitational dynamics. Black holes merge and emit gravitational waves that instruments on Earth can detect. Each of these phenomena reflects stable underlying relationships. The existence of law does not remove mystery, it frames it. It provides a structure within which deeper questions arise. The universe could have been different in ways that remain speculative, yet it is not chaotic in the sense of lacking pattern. It is coherent. In that coherence lies both explanation and wonder. The laws do not stand apart from reality. They are expressions of its structure, and within that structure thought itself becomes possible. The question that began this journey was simple in form and vast in scope. Why do physical laws exist at all? Along the way, patterns have appeared. Laws describe consistent regularities in nature. Symmetry connects conservation principles to invariance. Geometry shapes gravity. Quantum mechanics encodes probabilities with remarkable precision. Statistical mechanics reveals how order and disorder unfold over time. Information theory hints that structure itself may be foundational. Each perspective deepens understanding, yet none closes the inquiry completely. What is known with confidence is that the universe behaves in stable, mathematically describable ways across enormous scales. The same gravitational dynamics that guide the orbit of the Moon also govern distant galaxies. The same quantum principles that define atomic spectra in laboratories apply in the cause of stars. Conservation laws hold within measurement limits wherever they are tested. These regularities are not fragile or local. They extend across billions of light years and billions of years of cosmic history. It is also known that many laws can be connected to deeper structural principles. Symmetry explains conservation. Geometry explains gravity. Statistical reasoning explains entropy increase. Quantum field theory explains a vast array of particle interactions through gauge invariance and field dynamics. These are not arbitrary collections of rules, they form an interconnected network. What remains open is whether this network is ultimately necessary or contingent. It is not yet clear whether the values of physical constants are uniquely determined by deeper mathematics or represent one realization among many possibilities. The multiverse hypothesis offers one speculative path. Structural realism offers another philosophical lens. Informational approaches suggest that consistency constraints may lie beneath familiar laws. The limits of explanation remain visible. For every layer of understanding, a deeper question can often be posed. Why symmetry? Why mathematics? Why structure at all? Yet the persistence of these questions does not signal failure. It sharpens inquiry. It encourages clarity about what science explains and what lies beyond its current reach. Asking why laws exist refines scientific thinking. It prevents complacency. It reminds that equations are not merely computational tools, but reflections of stable patterns. It draws attention to the conditions that make prediction possible and understanding meaningful. There is also a quiet humility in recognizing that some aspects of reality may resist further reduction. The universe may contain foundational features that admit no deeper derivation, or it may yield further structure in time. Calm curiosity is appropriate here. The existence of law is not a dramatic anomaly requiring urgent resolution. It is the steady background condition of everything familiar. It allows stars to shine consistently. It permits chemistry to organize into complexity. It enables memory, measurement, and reflection. Living within such a universe means inhabiting a reality where patterns persist long enough to be discovered. It means that observation can accumulate into knowledge. It means that mathematics can map onto experience with striking accuracy. The question of why laws exist does not diminish this stability, it illuminates it. Perhaps the deepest insight is not that laws demand explanation, but that they make explanation possible. Without regularity, there would be no science, no inference, no reasoning from past to future. The universe does not appear chaotic in the sense of lacking structure. It appears coherent. That coherence may be grounded in symmetry, in information, in geometry, or in principles not yet understood. What is clear is that it is there, and in that quiet coherence, inquiry continues.